Okay, we're back. So as I was saying, my plan for today is to go over just kind of the basic operation of the FIB, the gas injector, the easylift needle, and then in terms of the applications to demonstrate, I was going to do a cross-section cut and a TEM lift out. Uh, do those plans work with the two of you? Because I want to make sure that I demonstrate the applications that you actually want to use the FIB for.
Yeah.
Yep, same for me.
Do both of you want to do TEM? Because I can spend more, I can spend more time on that versus other things.
I'm more interested in TEM.
Okay.
Yeah, so basically to prepare TEM samples and TEM. Yep, same.
Okay. All right. So I will then, I'll keep the other stuff pretty short because, to be honest, you see pretty much the whole operation of all these things doing a TEM sample. So I guess let's go ahead and get going here. Since both of you attended the intro training, I'm not going to go over basic operation of the tool, like how to turn the knobs or anything like that. But please interrupt me, ask questions if something isn't clear that maybe you missed from the previous training. I want to make sure I cover it. But this is going to be more of like an application style training as opposed to turn the knobs kind of training. But again, ask questions as you want. Let's see here. Oh, I guess I don't need this webcam anymore. I'm kind of in the way. So let's turn that off. All right, so just to start out here, I've got the chamber pumped down. I already loaded a sample into the system. The sample that's in here is just a little block of stainless steel that I have. The top has been roughly ground. I think I ground it through maybe like 1,000 grit sandpaper, but it's certainly not polished at all. But it's a sample I just had on my desk. I'm going to use it just for the today's demo. So we'll do a lift out from this, and we'll make a TEM sample out of it. It's probably not going to be a fantastic TEM sample because the top's not polished, but maybe it'll be interesting. You can see how far down the sanding damage goes into the metal and things like that. So first thing we're going to do is turn on the SEM. So we're going to click on quad 1 and then click on the beam on button. And that will energize the SEM. Now the topic of today is going to be FIB applications, but what I would highly recommend is don't turn on the FIB until you're ready for it. Especially when we're making TEM samples or atom probe samples, we want to avoid ion beam damage in the surface of your material. And the easiest way to screw up and wreck the surface is to image it with the FIB before you have your deposition layers down. So my advice would be don't even bother with the FIB until we get done with the other steps that involve the SEM. Just some other kind of housekeeping here. I'm just going to check the conditions of the system. I haven't used this yet today, so hopefully we don't run into any unexpected quirks. But I always take a look here. I've got a bunch of saved positions from the previous user. I'm just going to go ahead and remove those because I don't want to accidentally click on one of those and go to those spots. I'm also going to check my beam conditions. So I'm sitting at 5 kV. That's probably okay for now. 0.8 nanoamps, a little bit high beam current for my taste. So I'm going to drop that down a little bit. And when I loaded the sample, I used the plasma cleaner, and it looks like the software did not take the NavCam photo. So if this ever happens to you, it's really easy. Just go up to the stage and say, take NavCam photo, and this will go and reshoot the NavCam photo for us. I have seen the PFIB software can be a little glitchy, and sometimes when you go to take the NavCam photo like this, the software will kind of screw up. And if that happens now, we'll have to restart the software. I'm hoping it doesn't do that. That image looks very yellow or pink. I think someone might have some Photoshop stuff on there maybe. Defaults. No, the defaults are on. All right, well, that's going to bug me all day, the pink image. So the way to fix that is we need to give the camera more time to adjust the exposure. So instead of saying take navcam photo, we're just going to say move stage to navcam. And that will allow the navcam to be a live image, and it should adjust the color and be more normal looking. Or maybe it's not. Maybe it's going to stay pink all day. Drive me crazy. Yeah, there's no false coloration on the screen. That's weird why it's so pink. Well, anyway, I guess I'll just have to be annoyed, but I'll just have to be annoyed by it. Usually it's more of a white color, so take navcam photo. Yeah, we're running into some bugs here. So you can't see the status screen, but it's popped up a message here that says that it's not possible to finish the action. If you see it again, restart the server. Hopefully I can get my navcam photo. Oop. Rats. All right, well, I guess you guys get to see the tool restart procedure. But this is how it goes. These fibs are quirky. All of them, the Nova, the Helios, and the PFIB, they all sometimes have issues like this. But this PFIB software has been doing this to me frequently. So to restart, what we're going to do is we're going to close the user interface. Just hit the X up in the corner of the software. And then we have, yeah, see, anytime you close the user interface and you get these errors, it usually means something in the background had crashed. So we're just going to say close the program. And then we need to stop the server, which the server is this little floating bar up at the top. If you double click on it, it will expand into this kind of menu. And there's a start and stop UI button, and there's a start and stop server button. So we're just going to hit the stop button here. And that will shut down the microscope server. Which takes just a second. And then to add to the hassle here, the NavCam is a USB device that works through the computer. So when the NavCam is acting weird, you have to restart the computer usually to fully address any problems. You can't restart the computer with this server running. There's an interlock. So once the server is stopped, so it's fully shut down here, it says stopped and the start button is lit. Then we're just going to go down to our normal Windows and say restart. And let me turn the webcam back on just so you're not looking at a completely blank screen here. So a lot of times when I'm doing these kind of demonstrations, I like to come in a few minutes early and just reboot the computer as like a preemptive step. And I was running a few minutes late today, and I did not do that. And this is the price I paid. But I guess it's good for you to see this. This is this kind of stuff happens. I don't know what the computer is doing. It's doing some kind of backup. Come on. Well, I'm not going to wait for it. I'm just going to power cycle the computer with the power button. I think it was mad because I didn't shut down the open broadcast studio. The Windows was trying to remotely close it, and it was probably not happy about that. As we're waiting for these computers to restart, let's talk about some other things you need. When you come in to do TEM liftouts, you will have to bring TEM grids. The half grids are the style that are necessary for doing FIB liftout. You can buy those. We have a few in the lab that I can give you one if you need, but that is something that you would be expected to bring as a user. You also need some kind of a holder for your TEM grids. I have a couple of these holders in the lab that you're welcome to borrow for short time periods, but a lot of users will buy their own, and that way they have their own holders. So just keep that in mind, that we don't necessarily have all of the parts right here in the room for what you need. So make sure you know what you need before you come in for your session. Okay, so we've got our screen. We're not back live just yet, so I got to restart Open Broadcast Studio. Okay, what's going on here? Okay, so now we're back to our live screen here. Let me turn off my webcam. So the program to restart the FEI software is this icon right here. It's called XT Microscope Server. And we just go ahead and click on it, and that's going to open up the server program. Make sure up here all of these little green lights need to be lit. If any of these are gray, there's a communication problem between the software and the hardware, and it won't let you start the microscope. So if that happens, come ask for help. But in this case, you can see they're all green, and the start button is available. So we're just going to go ahead and hit start, and that will start up all of these little sub-programs that communicate between the computer and the microscope. So all of these things have to start up, and they first turn red, and then orange, and yellow, then green. So you have to kind of wait for all these things to cycle. It takes a minute or two. And because this auto run UI is selected right here, as soon as the server is running, the user interface should automatically start up. I would recommend anytime you're on one of these FIBs, whether it's the Nova or the Helios 650 or this tool, and it's doing odd things, so weird behaviors, anything like that, first thing troubleshooting step I would always do is restart the server and restart the computer. That addresses most issues that you're going to run into. And I've seen users work through weird behavior before, but in my opinion, it's not really worth the time. It's just take 5 minutes, restart everything, and your life will be easier. If you don't want to have this server window cluttering up your desktop, you just double click up here on the top bar, and that shrinks it up to the top. This can be moved around a little bit. Alternatively, you can also hit the X. If you close the server, it doesn't actually shut this program down. It just minimizes it down to the taskbar. So it's always going to be running down here in the bottom. So don't panic if you accidentally hit that X. It's not a bad thing. Okay. I don't know what that Windows message was. It's probably because I have Open Broadcast Studio running. Normally you don't see that. So then once the user interface is up, we're going to have to log in, and we're just going to use our standard login for MC2. I'm not going to say what the password is just because this is getting broadcast on YouTube, but you guys, if you don't know it, just come ask me sometime and I'll tell you what it is. Or Bobby or anyone. But it's our normal login. Okay, so let's get this out of the way. So when you restart the software, you'll find that the CCD camera starts out paused. So we always want to make sure that's live, just so we don't accidentally crash into something. And then let's see if our nav cam is working again. So we're just going to say take nav cam photo. And hopefully this works properly this time. Hey, look, it's working. And the weird pink color went away. So yeah, there was some kind of communication problem between the camera and the software, I guess, that is now fixed. Well, that's good. That pink color was going to drive me crazy all morning. Okay, so let's go back up here. We'll turn the beam on for the SEM. We're still at 5 kV, 0.2 nanoamps. And we can hit the pause button and we will start scanning. Now, I don't see anything, so I go to my lowest magnification. I'll adjust my brightness and contrast a little bit. And then let's use the nav cam to move around. So I'm just going to double click on the top of my sample, and we'll come over here to this surface. Now again, this surface is a little bit rough. I've definitely used this with some FIB cuts before. But first thing we always do is focus on the surface at least 2000x magnification. So I'm going to zoom in a little bit here, adjust my focus. And let me find something a little easier to focus on than that smeary stuff. I'm going to use my reduced area window. That always helps. Okay, that looks pretty well in focus. And then I'm going to link Z to FWD. I'll go to my navigation tab, and now I can set my height to be 4 millimeters. So we're always going to be working around 4 millimeters with the FIB. So we're going to type in 4, hit enter, and that'll bring the sample up to 4. Let me check my focus, and I'm going to repeat that link process one more time just to make sure that everything looks good. So back in focus, update my link, and you can see I was actually at 4.26. So I'm going to type in 4 again, enter, and now I should be much closer to 4. Now, for FIB applications, you generally want to get aligned with an edge of your sample, or at least with some kind of feature. So I didn't show this on the beginner training. A couple ways to move around. Let's say I want to have my sample parallel to this, whatever this thing is, this scratch or something. There's a couple ways I can go. I could just make a guess at the rotation. And let's say if I want that to be horizontal, I would say I need to rotate this about 45 degrees in the counterclockwise direction. So I can come over to my navigation tab. I can change my stage control to relative, and I can do a minus 45 degree rotation. Make sure the CompuCentric rotation button is selected. That will allow the stage to rotate around the center of the SEM image. Otherwise, the stage will rotate around the center of the stage rotation axis, which will cause this feature to move way out of the field of view. So we say go to, and that rotates 45 degrees counterclockwise, and it comes back up. And apparently my estimate on the rotation angle wasn't very good, because that's still not very square. The other way to do this, which is my preference, is to go to the stage drop-down menu, and we're going to use this first tool called Align Feature. We'll click on that, and Align, I clicked on the wrong one, Align Feature. And what this is going to allow us to do is either to rotate the stage or to use scan rotation to make a line on the screen, either horizontal or vertical. So this little window pops up. We're going to take the mouse, and we're just going to click and drag a line on the screen. The software doesn't care where you put the line. It only cares about the angle of the line. So don't just make it parallel to the feature you care about. If you need to, you can move it around a little bit more after it's on the screen. That's fine. You can see that it labels one point as 1 and the second point as 2. If we choose horizontal orientation, this will rotate so that point 1 ends up on the left side of the screen and point 2 ends up on the right side of the screen. If we do vertical, point 1 will end up at the top of the screen and point 2 will end up on the bottom of the screen. So be careful, you just pay attention to that depending on how you want the sample to flip around. So if I draw my line the way it is here, so 1 is on the left, 2 is on the right, this will rotate counterclockwise by maybe 20, 30 degrees. If I were to set it up the opposite way, so that 1 was on the right and 2 was on the left, this will rotate 180 degrees relative to what I just said, so that, again, when it's all done, point 1 will end up over here on the left side. And same thing with vertical. So point 1 always ends up on the top of the screen for vertical orientation. Okay, so let me get this line back aligned with that smudge, and then I want to do horizontal, and I click OK, and that will align it correctly. So the align feature is a much easier way to go. Now, I don't really care about this smudge. Usually I would align to the edge of the sample. So let me go ahead and do that. So here's the outside edge of this piece of steel. Again, I'm going to do align feature. I'm going to click down here and go this way so that this side ends up on the left side of the screen. And this will rotate around. All right. Now, one thing I should point out is you see when I'm rotating, the stage is dropping down about 7 or 8 millimeters before it rotates. That's because there's an option in the stage drop-down called Enable Safe Stage Moves. This feature is really nice to turn on if you have a rather tall, blocky sample, just because it helps avoid collisions when everything's rotating. Because my sample is so tiny and it's relatively flat, I'm not too concerned about hitting the lens right now. I'm going to turn this off because it's just going to add a lot of time to what I'm doing. Okay, so let's go back kind of to the middle of this piece. And the next step is going to be to find a very specific height on the stage that we call the eucentric height. The eucentric height is the center of the stage tilting axis. And the reason we want to find this height is it's the exact position where all the accessories are aligned and calibrated on the microscope. It's going to be fairly close to 4 millimeters, but it's never exactly 4 millimeters. So we always want to find this by tilting. The starting point is just find a obvious feature on your sample, whether it's a scratch, a pit, some kind of feature. It doesn't matter what it is, but make sure it's fairly distinct, and you don't look for like a 20 nanometer feature. Look for something that's a couple microns. So I'm just going to use this little dirt particle, or I don't know what this is. It looks kind of like a grease spot or something. And I just want to put that right in the center of the SEM. After I do that, I'm going to tilt the stage a little bit and we're watching to see, does this feature move up or does it move down or does it stay right in the center? So if this surface is exactly at the stage tilt center, so if it's right at the U-centric height, then as I tilt, that shouldn't move. So we'll come over here to tilt, and I'm just going to do 10 degrees as a starting point, and we'll hit enter. All right, and you can see that as the stage tilted to 10 degrees, that feature moved up a few microns. So what that tells me is my sample is slightly too tall, and I need to shorten it to bring that feature back to the center. To do that, we're going to use the Stage Z slider bar right here that's in the navigation tab. And I'm just going to click on the down arrow, and I'm going to bring that back to the center. And let's go one more there. Okay, that's close enough. Don't worry if the feature moves left or right. That's not important. That's there's actually a calibration that tries to fix that, but we don't care about that. We just care about the up and down shift. So now what I've done is fix the eccentric height between 0 and 10 degrees. But what we really care about is going from 0 to 52 degrees, which is the offset angle of the fib column. So I'm going to type in 52 and hit enter, and we'll continue up to that higher angle. If the microscope stage is really, really perfectly aligned mechanically, then the eccentric height between 0 and 10 degrees will be the same as it is from 0 to 52 degrees. But it's rather tedious to do that, and you usually will not find a fib set up that perfectly. So as you see, we get up to 52 degrees, and that feature dropped a little bit. So what we want to do now is do one more adjustment to the height. And again, only adjust the Z. We don't want to adjust X or Y by double-clicking. Only Z, bring that feature back to the center. And because we're tilted, the Z control will be a little bit more sensitive now. All right, close enough. So now just to demonstrate, let's just prove that we're right at the eccentric. I'm going to go back to 0, and we'll just try this again to show you how close we can get it. And sometimes it's a good idea to check this just to make sure you didn't do something wrong. It can drive you crazy if you think you're at the eccentric height, but you're actually not. So just good double check. So again, let's put that feature right in the center. I'm just going to use this little white particle in there. It's just a little bit more distinct feature. So that's right in the center crosshair. And then I'm just going to go straight to 52 degrees. And so if I have this done correctly, when it gets to 52 degrees, that feature should be real close to the center of the SEM image. And it's off by still a couple microns. So if I want to, I can nudge the stage up or down, but we're within like one click of the adjustment sensitivity. So this is very very useful you're very usable. We don't really have to get any closer than this. Okay, so now we're at the eccentric height of the stage, and from this point on, we don't want to move the Z control. We just want to tilt back and forth and leave Z alone because we don't want to reset the height. Actually, it would be a good idea. Let's just save our position. So I'll click Add, and now we have a saved position. You may find that you have to redo the eccentric height if you move around on your sample. So I don't know if you can tell on this particular block, I didn't grind the top very flat. So if I were to go down to this lower corner right here, that's probably a couple hundred microns taller than the surface that I'm working at right now. So if I do that, I'm going to have to refine the eccentric height in that location. It's not going to be the same because my sample is not flat. But if you're working on really flat samples like wafers or something like that, you'll probably find you're within a few microns of eccentric as you move around on the wafer. But it's easy enough to check your eccentric, especially if you start off at 0 tilt. So you just put a feature under the center of the SEM, tilt the stage, and if that feature moves a little bit up and down while you get to your tilt angle, just nudge the Z control, bring that feature back to center. And that way you stay right on eccentric. Okay, so the first thing we're going to do is we're going to deposit some material on this surface using the SEM. the reason we do this is we want to keep the fib damage out of this spot. So to do SEM depositions, we generally go back to 0-degree tilt. However, you can do SEM depositions at any tilt angle of the stage between 0 and I believe 60. You can't use the gas injector at negative stage tilt. The software has an interlock that prevents that, but 0 degrees is fine. And the first step is let's go ahead and put in the gas injector, and we can just kind of see what it does. So the gas injector control is this fourth tab down on the right called the patterning tab. And down here at the bottom, you have this area called gas injection. And the gas injector on the PFIB is called a multichem. And if I click on this little plus button, you can expand it. The multichem is really nice because it's a single needle delivery system that can hold up to 6 different gas chemistries inside of it. If you go to use the Nova or the Helios 650, you'll see that we have an individual gas injector for each chemistry. And those needles all come in on different ports and different angles, so it's a little bit, it can be a little more frustrating to use because they're always different angles. And the multichem, it always comes in the same direction. We have to insert the needle, and to do that, we're just going to select the insert checkbox next to multichem. And then if I hold the mouse over it, you see it says insert to default position. What I'm going to show you in a second here is the multichem can actually be moved around in the chamber, and it's going to go either to what it calls the electron beam position or the ion beam position based on your stage tilt. So because our stage is at 0-degree tilt, the multichem is going to go to the electron beam position. If we were at 52-degree tilt, it'll go to the ion beam position. So you don't really have to worry about that, but I'm just mentioning it as we're going through training here. So I'm just going to click on insert. And it says, do you want to insert on port 4? And say yes. Don't worry about the port 4 thing. That's just the designation of the mounting port on the multichem. The only reason it asks that is it is possible to have a system set up with more than one multichem. So the software is just trying to confirm that you want to insert it and to make sure you're inserting the correct one if you have 2. But to be honest, I've never encountered a FIB that had 2 multichems on it, but it is possible. So we say insert, and the multichem needle will come in right there. So here's the gas injector needle. It comes in pretty close to the sample, which is why we want to make sure we're at the eccentric height. This should be about 150 microns above the surface of the sample. So you make sure if your sample's got a lot of topography or pits or something like that, make sure you're not going to bump the needle into the top surface. But this sample's fairly flat, or at least flat enough that I'm not worried about it. So when we do the deposition, the gas will flow down the needle and it'll kind of cover this whole area of the sample with the gas. And then as we scan either the SEM or the FIB on the surface, that'll cause a local buildup of material only where the beam is scanning. And then when we stop the beam and turn off the gas injector, that rest of those gas molecules will just kind of evaporate and go out through the vacuum system. Now, if we want to move the multichem around, what you can do is right-click on the multichem control, and you can see there's a series of positions that I've programmed into here. The electron default and the ion default are the 2 positions that it's going to go to automatically. But I have a couple other positions in here. One is called FIB max horizontal field width. This just gets the needle out of the way. So if it's blocking your view, you can go to this spot. That would be getting it out of the way relative to the FIB image. So right now, if I were to turn on the FIB, I would not be able to see the multichem, which gives you the ability to do very large depositions. Some of the other positions are we've got this negative 38 tilt. This position is when you're using a negative pre-tilt holder, where you may find that the gas injector runs into the surface of the sample. As I mentioned earlier, the software won't let you put this the needle in when the stage is at negative tilt, or at least it usually doesn't, because it'll run into the sample. But if you insert the gas injector to this position, it should be okay. The other position would be the safe insert position. This is just like if you're really not sure what's going to happen, the safe insert position has the needle retracted almost a millimeter back away from the sample. And you can see here in the CCD camera, it's like a mile away from the surface. So that way, if you're worried about it bumping into something, you can always go to this spot. Now, if you want to use one of these positions, you don't click on this button directly. I just retracted the needle if you saw that. If I just click on it, it's going to go to the default position. So if you want to insert to one of those locations, you right click instead of left click, and then you can tell it to insert. So if I say I want to insert, say, to the FIB max horizontal field width, and I can right click and say insert to that spot, and that'll cause the needle to move to the position before it inserts, so that way it won't crash into anything. Or as I've showed you, you can move the needle around after it's in the chamber. So we can go back to the electron beam default. I would say 90% or more of the users on this tool are never going to use this function, but I think it's a really neat thing, and I like to show it during training. Okay, so we have the gas injector inserted, and the next thing we want to do is set up our electron beam conditions for doing depositions. So let's zoom in here a little bit. When you're doing SEM depositions, in order to maximize the efficiency and the deposition rate, you want to use a low accelerating voltage, and you want to use a high beam current. The low accelerating voltage is important because we want to confine the electron beam to the surface of the sample, because that's where the gas molecules are. If we use a high voltage like 10 or 20 kV, most of our electron beam current is going to be driven into the surface of the sample, and it'll just be absorbed as it scatters around in there, say as like backscatters or something like that. But it's not going to be very efficient at converting the gas molecules on the surface into a solid. So low accelerating voltage is key. What does a low voltage mean? I would say below 5 kV for sure. I generally do depositions at 2 kV, but if you're really trying to do a really thick deposition, I would probably go lower. You can go 1 kV, 500 volts even, and that will help speed up your deposition significantly. The downside is when you drop your voltage is you generally start to lose resolution of your SEM, and if your SEM resolution is bad, your patterns will have very fuzzy, soft edges to them, because the edges of the pattern are going to match the beam profile. So if you need a really sharp, square, corner type deposition, that would be the one case where you'd want to use higher voltages, just because it helps confine the beam profile. But that's kind of a special case. For just doing TEM prep, I would just go with 2 kV, and I think you'll be very happy with that. So we've changed, let's go to 2 kV on our voltage. And the other parameter we want to change is the beam current. The more beam current, the faster you'll be able to run. So if I'm doing a big SEM deposition, I'd be up here at like the 51 nanoamps or the 100 nanoamps, no question. If we're going to do a fairly small TEM sample, I don't think you need this much beam current. I think I usually will go with 13 nanoamps or 26 nanoamps, but it's going to be up to you. Be careful if you have a temperature sensitive sample like a polymer or some kind of like biologic sample or something like that, because that high beam current can melt the area or damage the area that you're working on. If you're working on metals, it's not going to matter. You're never going to hurt it. Another one would be bad would be any lithium containing material. Those high electron beam currents tend to cause the lithium to move around. So just watch out for that if you do have a sensitive sample. For now, let's just go with the 26 nanoamps. I like this beam current. I think it works well. When you change your beam current or your voltage, it's always a good idea to check your column alignment. So we'll go up here to direct adjustments, and we'll check our crossover. And that actually looks fine to me. I don't need to move it. But if your crossover or source tilt alignment is really bad, you'll lose a lot of beam current. So you want to make sure you're getting all your electrons down the column. You can also check your lens alignment if you care to, but with these high beam currents, it's probably not a big concern. Usually the biggest issue with the high beam currents is astigmatism. So I'm not even going to worry about that. What I am going to do is try to fix my astigmatism and my focus so my image looks okay. So focus, stigmator, stigmator, and that seems pretty okay to me. So let me just go back through our steps here as a summary. So we find our area, we put it to 4 millimeters, we use stage tilt to find the eccentric height, adjust only the z-axis to get at eccentric. We go back to 0-degree tilt. I set up my SEM conditions for deposition, so voltage and beam current, and I insert the multichem. Now we're ready to draw a pattern on the screen and actually do a deposition. The pattern control tab up here on the top is where you draw your shapes. So there's several different types of shapes available. Some of them are polygons, so you have rectangles, circles, polygons, and lines. Those are, I think, pretty self-explanatory. To draw one, you just click on it so that the shape is illuminated yellow, and then you just click on the quadrant, drag, and let go of the mouse, and that draws a shape on the screen. The other shapes are a little bit more specific. The cleaning cross-section and the regular cross-section are for using the FIB to cut out pits for preparing either TEM samples or cross-section samples, and we'll go through those in a second when we do the FIB stuff. Bitmaps allow you to import a picture onto the screen, and then you can mill that or deposit in the shape of that picture. I've seen this used for actual scientific purposes only a handful of times, maybe to deposit like an array pattern or something like that. Or I saw a paper a couple years ago where people used bitmaps to do like 3D milling to cut like a lens shape into a sample. Unfortunately, I would say a large majority of the bitmap patterns you'll see out there are people milling their university logos into samples, which I guess is neat, but it's not terribly scientifically relevant. And then the other one is stream file. A stream file is like a text file that has X and Y coordinates for the beam. So it's sort of like a script. You can use this to do very complicated beam paths. So say instead of just milling in an area like this in a square, say you want the beam to zip around in like a spiral or something as it goes through this shape. To do that, you'd have to write a stream file to actually map out the sequence of pixels as the beam travels around to get the beam to do what you want. So that's a stream file. So we're just going to do rectangle pattern. So I click, I drag it on the screen. If I need to resize it, I can click on the corners of the pattern and I can make it bigger or smaller. You can also click on these center positions and make it bigger or smaller in those directions. If you want to rotate the pattern, you grab onto this little arm hanging off the side. And when you do that, you can then click the mouse and then you can rotate the pattern around how you see fit. You can also set the dimensions over here in the properties tab in the pattern. So the X, Y dimensions apply to the shape. And if you go down here in the advanced properties, you can also set the rotation and the position of it. So let me set it back to 0 rotation so it's square with the screen. And for a relatively small cross-section on the PFIB, let's do something like, I don't know, 50 microns for X. And we'll do a couple microns for Y. Let's do maybe like 5 microns for Y. Now, by doing so, you see that the pattern is now larger than the screen. This will cause you an error if you try to run this pattern. So just make sure that you change your magnification so that the pattern completely fits inside the field of view. Otherwise, you'll get an error message on the software when you try to run it. The other things we want to do are we want to change the application file so that the software can predict what it is we're trying to do. The application files are specific to either the electron beam or the FIB. So when I click on application, it gives me 3 choices. carbon-M, which just means multichem carbon, and it's got an E, which tells me that's for the electron beam, or platinum M, E-beam deposition, or SEM marking. The SEM marking will just cause the beam to scan in this area. It won't open the gas injector. It won't deposit anything. In this case, we can choose whether we want to do platinum or carbon. I'm going to go with the carbon because I really like carbon. So I'm going to click carbon-M, and you can see the pattern changes color to orange. The orange tells me that this is a deposition pattern. If the pattern is yellow, it means that there's no gas chemistry, so that's usually a cutting pattern. So the pattern color can kind of help keep you from making a silly mistake. So we're going to do carbon-M. And the last parameter I want to look at is the Z value. The Z value is supposed to be the thickness of the deposition. The problem is, especially for the electron beam, it's not very well calibrated. When they build these recipes, they do this at a very specific voltage and beam current, and I believe it's done at 30 kV, which is not very useful. What you're going to find, especially for the SEM depositions, is that you don't really want to trust this number. It is useful for getting repetitive results. So if I put in 1 micron and do 20 different patterns, they'll all be the same thickness, but they're not going to be a micron thick. I'm just going to guess here, also because I don't want to waste a ton of time doing a deposition that thick. You see it says it's going to take 20 minutes for this. I'm just going to put in something small. Let's just try like 200 nanometers. Let's go smaller than that. Let's do 100 nanometers. And that says it's going to take 2 minutes. It's not going to be terribly thick, but again, I don't really care here. This is just a demonstration. The other thing I could do if I'd save time is I could make this pattern smaller. So for a given beam current, the larger your pattern, the longer it takes. So if I were to make my pattern 20 microns wide instead of 50, you see that my 100 nanometers now only takes 49 seconds, which is a little bit faster. How about we split the difference? Let's go with 30 microns wide, and let's make it a little bit thicker than this, 0.2 microns. So that says it's going to take 2 minutes and 27 seconds. I can adjust the position of the pattern, make sure it's where I want it to be. And then to start the pattern control, I'm going to go up here to the toolbar, and I'm going to hit this little triangle play button that says Start Pattern in Display 1. So I hit play, and now the gas injector is going to open. So if we look down here, you see the carbon is injecting, and my SEM is scanning only in this pattern area. And you can see if I adjust my brightness and contrast, it's giving me a live image only in this spot. Okay, so we have 2 minutes of just waiting here. I'm going to step out of the room for just a second. I'll try to be back right in 2 minutes, but if you need a quick break, we're going to have many times through today where we're just waiting on the FIB, so take breaks as you want. I will be back in about a minute and a half, I think, and I'm going to mute the microphone. All right, I'm back, and the pattern is done. So if we take, we just click on the pattern here, I can click up on the garbage can, or I can hit the delete key on the keyboard and I can remove that pattern. And if we take a look with our SEM scanning, we should now see a dark mark on the surface. That is the carbon deposition. It won't be very thick, maybe 50, 100 nanometers is what I'm hoping, but that's the idea. If I was doing a real sample, I think I'd definitely make sure that the deposition was over 100 nanometers thick. The goal of the deposition is to prevent the ions from the FIB from reaching the surface of your sample. So those xenon ions are going to get deposited a certain depth into anything they hit. And we want to make sure that the SEM deposition is thick enough to stop all of them so they don't actually get into the sample itself. So I think that's probably good for now for this demo. So I'm going to drop my beam current back down to something more reasonable. And go back down to 0.2 nanoamps. All right, and now what we're going to do is we're actually ready for the FIB. So we're going to have to tilt the stage towards the FIB column, which would be 52 degrees. However, to do that, we have to remove the multichem. The multichem, when it's inserted, locks the tilt and the rotation axes. So if I want to tilt, I have to take the multichem needle out. So I'm just going to click on the checkbox that retracts the multichem, and then we'll tilt the stage, and then we'll put the multichem back in. So we'll put that the carbon area right in the center, and then we're going to go to 52 degrees. And we can nudge our stage up just a little tiny bit here. It looks like we're slightly off eccentric. One thing you got to watch out for, especially if you're working with steel, is when you tilt the sample, if your sample has a little bit of magnetism to it, it can cause the electron beam to move around, and it makes it look like you're not at eccentric. And I don't know if that's what's happening here, but just one thing to be careful of. Sometimes you can end up going around in circles because it looks like your sample's moving, but it actually is the beam being pushed around by the magnetic field. If I want to take a nice pretty picture of this, we can turn on our dynamic focus or tilt correction if you like. The dynamic focus will allow the SEM to change focus from top to bottom as it scans along this, this tilted surface. So I usually turn that on. And then there's an automatic mode which will follow the original surface of the sample, or there's a cross-section mode, which once we cut the cross-section, we would use the cross-section mode, and that will follow that 90-degree direction of the surface. But I think you should use dynamic focus whenever you're working on tilted samples. Tilt correction, I find, is a little obnoxious. Tilt correction will stretch your SEM image up and down to try to make it look like you were looking at the sample straight on. If the surface is real flat, then this will probably make sense. But if you have topography on your sample and you use tilt correction, it leads to some really weird geometric stretching that I think is really confusing, and I would just as soon not do that. But that option is there if you want it. You can also put in pre-tilt. So if you're using a pre-tilt holder, you can tell the software that you have some pre-tilt angle on there, and that will recalculate the dynamic focus appropriately or the tilt correction appropriately. All right, so let's go ahead and turn on the FIB. So now I'm going to click on my FIB, and I'm going to go to beam control, and I'm going to click beam on. I could hit the wake up or sleep button, or the wake up button, but the plasma FIB, the wake up button, does the same thing as beam on. you'll see if you use the gallium fibs that they can be put to sleep and woken up to turn the emitter on and off for the fib. But with the plasma fib, the emitter is always activated, so we just need to click beam on and that's it. Now before I start scanning with the fib, it's a good idea to check your magnification. If I look on my SEM is at 3500x. And if I look on my fib screen, I'm at 224x. What that means is that if I start scanning with my fib, I'm going to cause damage over this entire area of my sample, which maybe you care about that, maybe you don't. But if you have a beam sensitive sample, it's a good idea to confine your fib damage to a relatively small spot, especially if you think you're going to have to do more fib work in like adjacent sites. You don't want to wreck your whole sample by taking one image at low mag. So I'm going to click on the fib and I'm just going to turn up, again, I didn't hit the pause button, I'm not live scanning. I'm just going to turn up the magnification until the fib reads about the same as the SEM. Now, I like to keep the magnifications independent between the SEM and the fib, but there is an option in the UI over here called couple magnifications that will force the SEM and fib to always have the same field of view. But for me, that drives me crazy. I don't like it, but you can feel free to use that if you want to. The other thing that I would recommend with the fib is try to avoid just live scanning with the fib as much as possible. It's much, much safer to use the snapshot tool because it allows you to take single frames of images. If I just hit the pause button, the fib is going to scan over the area 5 or 10 times before I realize what's going on, and I hit the pause button again. So that's going to cause a lot more damage to the surface. Whereas if you use the snapshots, you get one scan each time, and that usually is good. Let me check my snapshot settings. Hopefully, a lot of what I'm showing you here is going to be familiar from the basic training on the SEM, but as long as I have quad 2 selected, I'm just going to right click on the snapshot button. I'll say edit, and I'll go down here to my snapshot and just look at my settings. It's set to 300 nanosecond dwell. That's pretty good. I usually go for maybe 100 nanoseconds to about a microsecond. I find those are good scan speeds for the fib. If you're okay with a little bit of noise in your image and you want less damage on your sample, definitely aim more for like the faster scan speeds, like 100 nanoseconds. If you need a little bit more signal in your image, go 500 nanoseconds or a microsecond or so. That's going to be up to you. I'll just show you what 100 nanoseconds looks like. We'll hit apply and just make sure there's no frame integration on here. Okay. And oh, the other thing I want to look at here is my beam shifts. If I'm right at the eccentric height of the stage and I have my beam shifts kind of in the center of their adjusters, the fib and the SEM should be looking really close to the same features. So my SEM, if I right click on the adjuster and say 0, I have no beam shift on my SEM right now, and my crosshair is right in the middle of the carbon depth. If I go to my fib, I can see the last user had the beam shift over here in the corner. So that means my fib is probably not going to be looking at this spot. So I'm just going to right click and I'm going to say 0, and that removes any beam shift on the fib. Okay, so in theory, if the tool is really well aligned, if I take a snapshot right now, I should see the same image between the SEM and the fib. And let's see how good it is. So I take a snapshot, and I got an image here. It's pretty dark, but I can see the carbon bar right here. I'm going to turn up my contrast a little bit. I'm just going to blindly grab the contrast knob and turn it a little bit. You can kind of see the number going up here. And we'll take another snapshot. And, okay, not enough. Turn up the contrast a little bit more. All right, pretty good. So the alignment between the SEM and the fib is not perfect. We're off by maybe, I don't know, 5 microns or so here, but it's pretty close. Now, if I want the alignment to be really perfect, I'm going to use the beam shifter on the fib to move the fib image so that it matches with the SEM. You can do the opposite. You can move the SEM image to match the fib, but the fib has more beam shift range. So it's a lot easier to get the fib to point to where the SEM is looking than it is to get the SEM to look at where the fib is pointing. The best way I find to move the fib around with beam shift is to use the keyboard and mouse shortcut. I'm going to hold the shift key on the keyboard, and I'm going to left click the mouse, and I'm going to click on the center of the carbon deposition. So while I'm holding the shift and the click button down, you can see the mouse turns into a little hand icon, and then I can drag this spot to the center crosshair of the image and let go. So what I just did is I just beam shifted this area to the center, and then I can take one more snapshot to confirm that everything is correct and it looks good. The next thing we can do is we can check our fib focus and astigmatism. It's a good habit, especially on the plasma fib, is to do your focus and astigmatism adjustments at a known beam current, especially if you're going to use the big beam currents. And in this case, the anchor current that everything is related to is 30 kV and 0.10 nanoamps, which is actually where we're sitting right now. So if I adjust my focus and astigmatism at this condition, and then I change my beam current to another value, in theory, it should still be pretty close to focus and pretty close to the appropriate astigmatism. Now, if I have to be live scanning to do focus, but I don't want to scan over top of this area with the carbon because that's the spot I'm trying to keep preserved. So what I'm going to do is use my reduced area window, and I'm just going to draw a reduced area window kind of across the bottom of the image here, down in this material, which I don't really care about. And now I can go up and hit pause, and I can scan here as long as I want because I'm going to cut away all this material anyway. So I'm going to use the same adjusters for focus and astigmatism that the SEM uses, as long as the fib quad is selected, then it'll adjust the fib instead of the SEM. So I can do focus, and then X and Y stigmator. The fib resolution is notably worse than the SEM, so don't expect to see a really, really beautiful image. It'll just take some practice to get an idea of like what is good focus for a given beam current, but just keep that in mind. The fib resolution is nowhere near what the SEM can see. All right, that's about as good as it's going to get. Now, hopefully you can see here as the fib is scanning on this spot, it's starting to reveal some different contrast on the surface. That's because even with this relatively small beam current, it's sputtering away the surface of the material. And it's starting to reveal some of the underlying grain contrast or channeling contrast here. So the reason this contrast wasn't visible to begin with is probably because there's like an oxide layer on this surface and also some of the damage. But that just tells you that the fib always damages your surface no matter what you're doing, so don't image anything you care about. So I'm going to hit pause, stop my scanning. I'll click outside of the reduced area window to turn it off. Now let's do one more snapshot just to confirm everything looks good. Now we're going to go ahead and put in our gas injector. So we'll go back to our pattern control. And I'm going to click multichem insert, and the default position this time will be the ion beam default. So we hit insert, and there the gas injector comes in, and if we take an image, fib still looks the same. I'm not going to zoom out to look at the needle with the fib, but if I show you with the SEM, you can see here's the needle again inserted near the sample. All right, so now what we want to do is choose our conditions for doing the fib deposition. 30 kV will work for fib depositions on the PFIB, but it's not ideal. The xenon in the fib, or the xenon ions that we're using to cause the deposition, will become implanted into the growing film. And they will basically turn into little bubbles or little voids in the deposition. And when you go to cut through that film with those little bubbles, those will act as little point sources for artifacts, and your fib cut will not be very pretty. The way to get around that is to use lower accelerating voltage for the fib deposition. And if you look in the pattern, let's just draw a pattern on the screen. So a rectangle pattern. The application files available to the fib, there is a carbon-m 12 kV file. And that one is actually from Thermo Fisher. They created that one. But the reason it says 12 kV is that is Thermo Fisher's recommendation for a good voltage for doing depositions. And they told me during the live training, somewhere like 8 kV to 12 kV is good, depending on what you're trying to do. But just keep that in mind. If you do a 30 kV deposition on the PFIB, you're going to have little bubbles formed in your deposition, and it'll cause problems, or it can cause problems. So my recommendation is let's turn the voltage down to 12 kV on the fib. Now we're going to do our fib cuts at 30 kV, but we're going to do the deposition at lower voltage. Now the other thing we need to look at is what material do we want to deposit. We have carbon and we have platinum on this tool. And you have application files for platinum-M, and then there's a couple kind of specialty ones here that are they just changed some of the advanced properties in the pattern file. And then you have carbon, and then we have this carbon plus platinum file. The xenon ion beam will deposit platinum just fine, but the problem is that platinum is really soft in the plasma fib. Now this is a very different behavior than what you'll see on the gallium fib. On the gallium fib, the platinum deposits and it's very hard and it makes a very good protective layer. For the plasma fib, the platinum will erode extremely rapidly. So if you're going to use platinum, you have to make sure you have a lot of it. And by a lot, I mean 5 or 6 microns at least if you're doing TEM sample. Otherwise, you will lose all of your platinum capping layer before you get your sample thin. The carbon by itself, when it's deposited by the fib, has the opposite problem. It's really, really hard. It's almost as hard as like diamond. And if you deposit carbon and then try to cut through it, it's almost it's really frustrating because it doesn't cut very cleanly and it just takes forever to cut it. That being said, the best approach is to use the multichem. We can blend the two gases together. So if carbon is really hard and platinum is really soft, if you mix the gases, you can actually tune the hardness of the deposition to match your sample, which is a really neat feature that only the multichem lets you do. So if you pick the carbon plus platinum file, and we look down in the advanced settings here, it's going to do 2% flow rate on the carbon and 100% flow rate on the platinum. So just that little tiny extra bit of carbon gas added to the platinum makes it behave much better. Now, if you want it to be harder, you can add more carbon. So I would say 3, 4, 5% carbon, something like that, would make the deposition much, much harder. So if you're working on a tough to cut material, say tungsten or some of the oxide materials, boron nitride, something like that, you might want to have like 3, 4, 5% carbon in the mix. If you need your deposition to be soft, dial that back a little bit. Maybe go with like 0.5% or 1% carbon. And the goal is you want the capping layer to be a similar hardness to the material you're trying to cut. I'm just going to go with 2% carbon because I'm pretty sure that'll work fine, but feel free to change those. So if I go in here and I just change this to some other value, that'll change the ratio of the gas mixture. That will not overwrite the application file though. So this carbon plus platinum apps training, if I delete it and draw it again, it'll go back to 2% and 100% for platinum. So we're going to go ahead and use that. The last thing we want to check is our beam current. We want to make sure our beam current is appropriate for this size pattern. And the best way to calculate that is based on the area of the pattern. So if you figure out the pattern area in square micrometers and multiply it by 6 picoamps, that gives you an approximate beam current to use. So in this case, our pattern is 30 microns in X, and we're going to do 5 microns in Y. So if I pull up my calculator, so we're going to do 30 times 5. So our pattern is 150 square microns in area, and then we're going to multiply that by 6 picoamps. So times 6, and that gives me 900 picoamps. So a good beam, or a optimum beam current for this size pattern would be 900 picoamps of beam current. Now we're currently imaging with 0.1 nanoamp, which is 100 picoamps. So right now my beam current is way too small. So what I want to do is, now that I know what my optimum beam current is, I want to go find the closest beam current in the FIB relative to that. So we're at 100 picoamps right now. We have 330, and then we have 1,000. I'm going to go with the 1,000 picoamp condition. It's slightly higher than my optimum beam current, but that's okay. It's not too far off. So we get up to 1,000 picoamps. And it's going to be a good idea to take one snapshot just to make sure that everything looks okay on my image. But in theory, our focus and astigmatism should be pretty close. So let's go ahead and we're going to say snapshot. And I see that my image shifted a little bit. So this particular voltage and beam current, the beam shifts off a little bit. So I need to fix my beam shift. And I'm going to use that same shift and mouse click trick. So I'm going to shift. I'm going to click on the center of the carbon bar, drag it to the center of the screen, let go. We'll do one more snapshot. And that actually, I think I went too far here. Let me turn my contrast up a little bit. Try that again. I'm going to drop my magnification one click here. Oh, I know what's going on here. I'm looking at the, this is the mark from cutting where I'd focused the 100 picoamp 30 kV condition. I thought that was the carbon bar. This is actually the carbon up here. Now this looks a little bit out of fuzzy and out of focus. I think it might be a good idea to try to get this a little bit better in focus. Let me hide my pattern, and we'll do reduced area again right here. Let's go to full screen by hitting F5, and let's see if we can get this a little bit nicer. So focus. Oh yeah, the astigmatism is pretty bad. So let's fix the astigmatism. All right, that's about as good as that's going to get. We'll do one more snapshot. And so I'm having a hard time seeing the carbon bar. And this is where I mentioned that 100 nanosecond setting for the snapshot can be a little on the fast side. So if I edit my snapshot to be a little bit slower, let's try like 500 nanoseconds. You can see the image quality is a little bit better. And if I kind of squint at the screen, I can see here's the carbon bar right there. So let me unhide my pattern, and I'm just going to slide that up on top of the carbon. And now we can go ahead and hit play again. How thick we want to deposit is going to be dependent on what you plan to do here. For just a simple cross-section, I would say a micron is fine. If this is going to be my TEM sample, then I would probably go with a little bit more, maybe like 2 or 3 microns, just to make sure you don't run out of capping layer. What I'm planning to do here is I'm going to use this as a cross-section demonstration, and then we can go ahead and use this also for the TEM lift out. So let's go ahead and make this a little bit on the thicker side. Let's go like 2 microns. And that should be, actually it'll end up being thicker than 2 microns because this application file is not really well calibrated. And I'm going to go ahead and hit play. Oh, and I get this message that pops up. This is good that this happened. So anytime you see this message, it's telling you that the beam current, when the FIB measures the beam current, it changed a little bit. So it calculated this pattern time based on the initial beam current. And it's telling you that you should recalculate this number. So when I hit recalculate, it's going to change. Instead of 11 minutes 32 seconds, it'll be something else. So I hit recalculate, and it dropped down to 10 minutes and 4 seconds. So that just says that the FIB beam current, it rose a little bit between when I drew the pattern and when I hit play. But we should be okay now. So let's hit play. All right, so now the FIB is scanning, and we're injecting 2% carbon, 100% platinum. Now, if I want to see what's going on, I'm going to go back to my quad view, and I can use my SEM to take snapshots. So now if I go over here and hit snapshot, I will get a really out of focus image. Let me pause my FIB scanning for a second. I'm going to fix my SEM focus because this is really bad. All right, so let me hit resume patterning. So if I hit snapshot again, I will get an updated image as that pattern or that platinum is growing. And I can watch the progress as it goes. All right, so here's another time. We've got 9 minutes and 20 seconds to wait. So I will, if you guys have any questions, now would be a good time. If you don't have any questions, I say let's just take a break. Okay, okay, question says, is it a good rule of thumb for all materials, or are there any exceptions? Was that about the depositions? What was that question? Yes. Yeah, so a couple microns is a good for pretty much anything. The harder the material you're cutting, usually the more deposition thickness you need. But I'd say 2 microns is a good starting point. It also it depends a little bit on your skill as a FIB operator. That if you're not real good at getting the FIB focused and placing your patterns, you generally will lose more of your capping material as you cut the cross section or cut the TEM sample. So you might want to start off with a little bit more thickness until you kind of figure out, how it goes. On the gallium fibs, the beam is much more accurate. It's much more easy to focus. And you can do TEM samples on a gallium fib with only a couple hundred nanometers of capping material if you're real careful. But on the plasma fib, because the beam has a really, really big profile to it, you want at least a couple microns. So let's just see what happens here. So I set it to 2 microns. I actually think it'll be more. I think it'll be more like 3 in total thickness when it's done. But we'll see how it turns out, and you can get an idea from there. The real key is that when you're making a TEM sample, especially, is you want to have some of that capping material remaining on the sample when you're all done. So if you're going through your process and all of your capping material gets sputtered away before you get it as thin as you want, then on your next sample you need to start with more. Or if you get all the way to the end of a TEM sample and you still have like 3 microns of this platinum carbon mixture left, then you could probably back off the thickness a little bit and save yourself some time. Unfortunately, the deposition step is one of the steps that really you can't speed up, because even with the high beam currents on the plasma fib, we're limited by how much gas can be delivered by the multichem. So you're always looking at somewhere around 4 to 6 minutes for a micron of growth, no matter what beam current you use or what size patterns you use. So this step, if you're doing 2 microns, you should expect at least 10 minutes or so to be waiting around. All right, I'm going to set a timer for myself for 6 minutes, and so and I will come back in a couple minutes, and I will see you all back in about 6 minutes then. Okay, I'm back. Looks like the deposition's finished. Let's take a look at what we got here. All right, so we got a nice blob of platinum and carbon on the surface here. And if I measure the thickness, let's put a little measurement bar on there. Go from center to about the center, something like that. And I need to change it to be cross section. And it looks like it measures around maybe a little bit under 4 microns thick, maybe 3.5 microns thick. So again, this application file, maybe not the best calibration because I set it to do 2 microns and it's a little under double that thickness. But this should be plenty for what we're trying to do. And it only took about 10 minutes. So we're done with the multichem for a while. So we're going to go ahead and retract the multichem. So I just click on it. We'll take it out. And we're going to move the FIB back up to 30 kV for doing our cuts. So I'll go up to the FIB voltage, change it back to 30 kV. And let's set our beam current back to the 100 picoamps. And let's delete this pattern. We don't need it anymore. And it looks like I lost my image. So we're having a service problem on this tool right now. And what happens is that when you change the beam current on the FIB, there's different, an aperture is supposed to move an aperture strip to different size holes. And the problem is that the motor is slipping and it's getting stuck. So right now we're basically, the beam is getting blocked. It's not going through the holes. The solution to this is to either go up here to the the beam tab and try to home the FIB apertures, and that sometimes fixes this problem. Or what we can also try to do is just move between like the small and a big beam current a couple times, and hopefully the FIB motor will get unstuck, and then it'll start moving correctly. So let's just try to run let's try doing that first. Let's just go up to like 0.5 microamps. And if everything moved correctly, if I look down here on the bottom where it reads out my beam current, oh, you can't see that. I need to adjust the display slightly. Oh, I must have moved my image slightly earlier. Okay, so if you look down here on the bottom, it says that my beam current is 500 and something nanoamps, and that's what my setting says up here. That tells me that the aperture actually moved to the correct spot because my beam current matches the setting. So now let's go back down to the 100. And as long as this reads close to the right value, we should be okay, and it's not. It's reading 124. That's close enough, I think. So now if we take a snapshot, we should get our image back. And there we go. Again, beam shift, click, drag to the center. We fix our beam shift, and everything looks good. Now, from this point on, because we have this carbon deposition on the surface, I can be a little bit less cautious about causing FIB damage to my sample. But if you're going to do check your focus and things like that, it's still a good idea. You know, use reduced area and keep the beam off of anything you care about. So reduced area, we'll check our focus. And astigmatism. Okay, So now we're getting to the point where we want to do our first big fib cut. The pattern we're going to use is called a regular cross section. So I'm going to go to the pattern tab, and I'm going to select regular cross section. And this, you click and drag this like a rectangle pattern. And I'm going to put it on the bottom of the lift out. And I know I need to drop my field of view a little bit here. All right. And let's take another snapshot. Rule of thumb is to make your pattern about 5 or so microns wider than the deposition. Maybe a little wider is good if you're using one of the really big beam currents, but in this case, my deposition was 30 microns. So let's just make this 5 microns wider in each direction, so that would be 40 microns total width. The Y size and the Z size, I'm going to change based on how deep I want to cut. I'm going to try to make a 45-degree slope cut, so I want them to be roughly the same. The catch, though, is that this pattern is calibrated for cutting silicon, and the material I'm on is steel, which will cut a little bit slower. Set my Y size to be 20 microns. I think that'll be a good number. And in silicon, I would set my Z size to also be 20, and that should cut about a 45-degree angle cut because the two parameters match. However, iron samples or steel, they generally cut a little slower than silicon. So instead of cutting 20 microns deep, I think I need to change this and maybe cut something like 30 or maybe 35 microns deep. I'm actually not entirely sure what the best value is, but let's just try 30 microns and we'll see what happens. Now when I do that, it says that this is going to take 44 hours and 48 minutes to make that cut. Now, if you really, really want to sit here for 2 days or so, you're welcome to do so, but the solution so that this doesn't take forever is just turn up the beam current. The plasma fib has beam currents available all the way up to 2.5 microamps. And I don't know if we need that much beam current for this, but don't hesitate to use big beams to cut this type of thing. So if let's hop up to the 0.5 microamps and let's just see what that says. So if I go to 0.5 microamps, it says for this cut it's going to take 47 seconds. That's a lot better than the 44 hours. Now we do have to be a little bit careful. These large beam currents are easy to blast your sample and wreck your region of interest. So definitely go with the snapshots with these big beams. So I let the beam current change, and I can do a snapshot, and I get an image. Now, one thing I should point out is, if you notice there, this thing inserted over the sample, this is called the shutter. Basically what it is just a big block of metal, I think it's molybdenum, with a hole in it, and it goes in front of the fib. So the fib beam is passing through the hole and still hitting the sample, but the idea of the shutter is it helps prevent some of the material that gets ejected off the sample from sticking to the bottom of the SEM lens. So that'll go in and out automatically. Don't worry about it. It only applies to the largest beam currents. So it only happens for the 0.2 microamp, 0.5, 1, and 2.5 microamp beams. If you're using 60 nanoamps or less, it won't insert. So I can't see anything on my fib image. I think I need to turn up my contrast a little bit and turn it up even more. Oop, too much. Turn it back down a little bit. Okay, there, I can see my deposition, right? So now I get an idea of where I have to put my pattern. So I'm going to slide my pattern over a little bit. I could also fix it with beam shift. I could beam shift this back. These large fib beams are notoriously hard to focus. So this is where I definitely recommend adjust your focus at the 100 picoamp beam. That's a 30 kV 0.10 nanoamps, and go to these big beams and just trust the alignment of the tool and just cut. You're gonna get yourself probably into more trouble if you start fiddling around with the focus and the astigmatism on these. And to be honest, it's not that sensitive. It's not that critical. But just get used to the idea that the image is going to look kind of fuzzy even when it's in focus. Now, if I want to make sure I actually have a good beam, the best thing to do is called a spot burn. So if I go up here in my toolbar, I have a button called spot mode. And what I'm going to do is I'm going to basically park the beam down here somewhere where I don't care about, and I'm going to let the beam mill a little hole into the surface. And when I look at that, it's going to tell me what size is the beam, what shape is it full of astigmatism or not, and like what is the quality of that beam. So the way we do this is we're going to enter spot mode by clicking the spot mode button, and you see the beam blanker turns on automatically. And then I'm going to drag, I'm just going to click and put the spot somewhere where I don't care about, like right here. And then I need to turn off the beam blanker, which if I go up in the toolbar, there used to be an icon up here. It looks like it's been moved. We could bring it back by customizing the toolbar, or I can go to the beam tab, or sorry, the scan tab, and we have the beam blanker button right here. There is a keyboard shortcut for it, Control B. So I'm going to turn off the blanker for about a half a second, and then I'm going to go back to full frame mode right afterwards. So I'm going to turn off beam blanker, and then I'm going to go to scan and go back to full frame. So that should have put a little hole right here in the sample. Let's take another snapshot, and we can see, okay, there's a hole there. It's kind of blurry, but it'll probably show up better with the SEM. All right, so that's the half a microamp hole. It looks like the aperture is a little bit out of position, and the only reason I can tell that is you got this sort of little tail on the side of the hole. Maybe we can fix that by, again, I gotta move the apertures around a little bit. So let's go back to a small beam current, and then back to the 0.5 microamp. There we go. So now my beam current is showing the correct value. Let's try that again and see if I get a nicer hole. All right, so we go to spot mode, put the beam right there, scan, beam blank, scan, full frame. Yeah. Well, you can see that the problem we're having here is because the aperture is not moving to a consistent spot, that before this little tail was up here on the top right of the spot, and now it's over here on the top left. And that, again, that's just because the aperture is slipping on and not going in consistent locations. So this is really frustrating for us. We're trying to get this fixed, but this is a problem. I think what we're just going to have to do is go with it and move forward with this cut. But this gives us an idea of how big the beam is. So when we go to make our actual pattern placement, we want to keep in mind how large that diameter is. The center of the beam is going to go right down the center line of this yellow bar. And my pattern, here, let me put a circle on here. Right, that's about the diameter of my beam. It's about a 10, maybe 12 micron diameter circle. So if I were to put my pattern right up next to the platinum, that means that that big beam is going to cut away more than half of my region of interest. which is not going to be a good result. So because I know kind of how big my pattern is, or I know how big my beam is, I want to back off my pattern a little bit so that I don't wreck my lift out. So I would say something like this is probably good. I need to back up my field of view slightly. And this way I will get my fib cut and it should avoid wrecking the side of my sample. Now I'm demonstrating a cross-section cut right now, but if for TEM, what we would do is place another one of these patterns up on the other side and do 2 cuts at the same time. And actually this is going to go so fast, maybe I should just do that right now to save some time. So what I'm going to do is copy this pattern by doing Control-C. So I select it, Control-C on the keyboard, and then Control-V on the keyboard. And then here's the second pattern. I'm going to put that up on top. And I'm running, I need to, again, all my patterns have to fit on my field of view. Let me move my little measurement circle up here. Something like that. And I need to make this pattern flip around. With the regular cross-section cut, the heavy yellow line is going to be the deep side of the cut. And the thin yellow line is the shallow side. So I want the deep side of the cut to be right next to the deposition. So I'm going to click on pattern 2, and I'm going to change the scan direction instead of bottom to top to be top to bottom. And now the deep end of this pattern will be adjacent to the deposition as well. So this should be pretty good, and let's go ahead and run it, and we'll see what happens. So I'm going to hit play. Oh, recalculate our pattern time. Let's hit play. And we should be cutting. All right, so pattern 1's done, and then pattern 2 starts right automatically. Okay, all done. Let's take a look with our SEM and let's see what we did. So now we've got 2 pretty big holes in the surface of the sample, and you can see that my cuts did not get up right next to the platinum deposition, which is good. That's what I wanted, because we're going to use a second cut to get right up next to that surface. So that looks good. So I'm going to go ahead and delete these patterns. I don't need them anymore. And for the cleanup cut, I don't want to use this same big beam current, right, the 0.5 microamp, because I'm going to get the same cut quality as I'm getting right here. I want to drop my beam current down to get a better edge result. So rule of thumb would be, and this is not, not a hard rule, but whatever beam current you use for your regular cross section, drop down 1 or 2 beam currents for your cleanup cut, and that should work pretty well. So if I did my first cut at 0.5 microamp, maybe drop down to like 60 nanoamps for the next cut, and that way we'll see what the cut quality looks like. So now I'm going to go back to my FIB, and I'll take a snapshot. I'll adjust my brightness and contrast a little bit here. So I can see where I need to cut. Let's do a test spot. Let's see what this beam looks like. So if I say scan, we'll go to spot mode. Now, to move the spot, right now I have my pattern control activated, so the software thinks I'm trying to draw shapes. I have to go back up here and click the mouse icon, and that gives me control to move the beam spot around. So I just put the spot over here for a second, and go to scan beam blank, and then scan full frame, and let's take an image. And you can see that the spot at 60 nanoamps is quite a bit smaller than it was at the 0.5 microamps. And if I look at it with the SEM, you can see that the edge quality of that spot is much, much, much better. So smaller beam currents are good for these cleanup type cuts, whereas the big beam currents are good for making big holes. So what we want to do now is we're going to use a different type of pattern called a cleaning cross-section. And the cleaning cross-sections are used for this exact application where you have a little bit of an edge on the sidewall of a pit, and we want to remove that. So the regular cross-section is done first to make the pit, and then the cleaning cross-section is done to remove this material here. So I'm going to go ahead and draw that pattern over top of the remaining material. I can set my dimension to be that same 30 microns, or sorry, 40 microns. The Y size is not a specific number. I want to set the Y value based on how much of this material needs to be removed. So if I left myself more material, I might have to make this taller than it is right now. And then the Z size, I'm going to use the same Z value I used with the regular cross section. The cleaning cross section and the regular cross sections have been calibrated, so they should cut the same depth. So if I cut 30 microns with the regular cross section, I can cut 30 microns with this one, and I should get about the same result. And I can have the pattern up pretty close to the platinum this time because this beam is a little bit easier. It's a little bit more precise. I'm not too worried about blasting a lot of my platinum this time. So we'll do something like this, and we'll hit play. Cleaning cross sections, it cuts line by line from the bottom of the rectangle going in the up direction. So it's sort of like a meat slicer or something. It's just kind of shaving off this edge as it goes. Whereas the regular cross section cuts over the area over multiple passes, and it actually slows down the cut as it gets towards the top, which is how it makes the sloped cut. And let's just check on our progress here. We'll take a snapshot with the FIB, and you can see where we're moving that edge upwards. All right, let's see. Take a look with the SEM. one of the quirks with the plasma fib is that with these big beam currents, the plasma fib puts out so many secondary electrons that it kind of saturates the electron detectors. So if you're using the big beams like 60 nanoamps and up, when you take images with the SEM, you'll see that they always start out really saturated, and you have to give it a few seconds for everything to kind of settle down, and then you'll be able to get an image. So we have an okay cut quality here. Not great, but if this was for a TEM sample, I wouldn't worry too much about this. I'd just go for it. This first demonstration is I'm trying to make a cross-section type cut, which in that case, we do want this finish to be really nice. So what I'm going to do is we're going to have to do another cut and try to clean this edge up a little bit more. But since I'm kind of simultaneously making a TEM sample and also a cross-section at the same time, let's go back to the fib, and I'm going to cut the backside cut as well. So I'm going to drag my cleaning cross-section up here to the other side, and I'm going to change that scan direction to be top to bottom, and I'm going to hit play. Let's do one more snapshot just to make sure, and we'll hit play, and that way I'll cut that backside at 60 nanoamps. And then for the cross-section application, I'm going to drop my beam current again on the fib, and we're going to try to clean up the front face a little bit more so it looks good. And again, with these FIB applications, there's quite a few times where you're just going to be sitting and waiting for something to happen. So, you know, it's nice to bring a book or bring a phone or something to play with, because I've seen some of these FIB cuts, they might take 20 minutes or more, and you know, you get bored sitting here staring at the wall. For this training, I'm trying to use the fairly high beam currents to keep it going efficiently, but we still have to wait for these cuts to proceed. All right, let's see what we got. So now we have our cuts on both sides. We'll get back to this step, but for the TEM lift out application, the next process would be to do the cuts on the sides and across the bottom to get this ready for picking up with the easylift. But we're going to stop right here and do the cross-section cleanup. So the goal is we need to make this front face look prettier so that we can actually see the microstructure, which you can kind of see it in there, but all these little curtain artifacts are going to get in the way. So let's drop our beam current down again. Let's go down to the 15 nanoamps. Let's see if this is a small enough beam current to get a nice result. And let's take an image with our fib. And I need to get my contrast adjusted so I can actually see where the edge is. That looks pretty good. And we're going to use this same cross section, and this time we're just going to try to remove just a little bit more of this material, and hopefully that'll get a nice face quality here. So we'll just do something like this. All right, and let's hit play. And we got 2 minutes and 30 seconds, so I guess I'll see you in 2 minutes and 30, and we'll see what the result looks like. All right, let's see what we got. All right, so not great, but not terrible, I would say. Let's go back up to a little bit higher voltage. I think we'll get a little nicer image quality. Just because we're looking at steel here. All right, now if you can see here, there's quite a bit of artifacts on this surface. Lots of these little vertical stringy things that we call curtains. You can see some of the grain structure over here, but this is not, I would say, not really fantastic in terms of a cross-section quality. And this is one of the things that makes the PFIB a little bit different than the gallium fib is that you have to come up with ways to deal with this. Having more of a more thick platinum cap definitely helps. You can see that there's relatively flat below this, but one of the approaches that we're going to try is we're going to cut this on two different directions, and you can call this like a rocking FEI or Thermo Fisher calls this a rocking polish, or you can call it like cross polishing or something like that. But the idea is that the fib is always going to generate these little vertical artifacts. And if you cut it on two opposing directions, for example, you cut it this way and you cut it this way, those artifacts cancel each other out and you end up with a really nice smooth surface. So I'm going to leave the fib at this relatively high beam current, and I'm going to show you just how to set this up manually. There is a wizard in here. If you go to the 5th tab, it's called Rocking Polish. This will basically do what I'm going to show you automatically, but it requires a fiducial, and I don't really want to cut a fiducial into the side here. So let's just see what we got. What we want to do is we want to turn the stage 90 degrees. So first of all, I'm going to save my position because I know I need to come back to here. So what I'm going to do is I'm going to do a relative 90-degree rotation. So now the fib will be seeing a vertical edge, right? But the fib is still looking top down over the sample. So if I cut this with the fib, I won't see anything different. Now what I'm going to do is I'm going to go back down closer to 0 degrees. So let's go back to maybe like 30-degree tilt. You don't have to go all the way to 0. Just as you change this angle, you're changing the polishing angle for the fib. So let's try something like this. And then you can also turn the sample slightly into the beam. Let's turn it in maybe like 2 degrees. So I'm going to do like 2 degrees. So now that because the fib is kind of coming in like this way now. Let's take a look with our fib image. So this is the face we're trying to clean up. And what we're going to do is I'm just going to use a rectangle pattern. Don't really need a cleaning cross section for this. Make that pattern kind of parallel with that edge. So something like this. And what I'm going to do is I'm just going to run this pattern for a couple seconds. And then we're going to flip the sample around 180 degrees. We're going to do the same cut on the other direction. And that'll be those two opposing cuts. So let's hit play. We'll let that scan for, let's let it run for, we'll do 1 micron if it was silicon. That's going to be 11 seconds. Okay, let's add this position. So this is going to be rocking cut 1. And then we're going to do a relative 180 degree rotation from here. And I need to do my little 2 degree offset, which is, I've got to undo the other one, so I actually need to go 4 degrees. I'm going to say add, rocking, cut 2. So on this position, make my pattern aligned with the edge. Actually, here, before I do this cut, let's go back to our position 1 and look at it. And we should see the fib artifact lines should be going on an angle now because I cut it on kind of that cross direction. And actually, you can see it's already a lot smoother than it was. So actually don't really see the angle cuts too much there, but you can see how that even 1 10-second cut just from an angle here, it kind of polishes out those vertical artifacts. So what we're going to do is we're going to go back and forth a couple times, and that should clean up this face real nice. back to cut 1. So let me just I'll do 2 cuts in each side, and then we'll go back to our imaging and see what it looks like. When you're doing this, because I have both sides cut, it's a little bit awkward. You got to remember which side you got to cut on. But normally for a cross section, this pit wouldn't be there, so it's really obvious which face to cut. All right, let's go back to our spot here and let's see what this looks like. And that looks pretty nice. Most of the contrast on a smooth face like this is going to come from channeling contrast, which I think we need a little bit more beam current to pull that out. So let's kick up our beam current a little bit, and here, let's drop our voltage down. I don't think we need to be at 5. Let's try 3. And let's check our column alignment. Okay. That looks pretty good. Check our focus. Astigmatism. All right, and now let's, we want to do dynamic focus again, but this time we want to be using the cross-section mode. We can slow our scan speed down here. And if you remember from way back at the beginning of the training, I told you this sample wasn't polished. I just ground it with sandpaper to like 1,000 grit finish. And you can really see the extent of the damage when you do that. Let me get a nice, really slow scan here. Sorry, this is my inner metaler just coming out now. So up here on the top, first of all, there's like an oxidized layer, which is this, I think, this kind of garbagey layer right here below the surface of the carbon and the platinum. And then below that, we've got a nice big grain here of iron. But you can see there's some contrast in there, which is all like from damage, dislocation, stuff like that. And all the contrast between the various grain boundaries is all obscured. So all of this stuff in here, this is all from damage from grinding it. Whereas the undamaged material down here in the lower part of the pit, I would have expected this kind of contrast to be right up here near the edge if this wasn't completely mangled. But again, this sample wasn't prepared correctly, and I kind of did that on purpose, so we'd have something kind of fun to look at. So anyway, that's the idea with the rocking polish, and now you can actually see here the 2 different angle cuts, right? So I've got a cut going this way, and I got a cut going this way, and they kind of cancel each other out, and you get a really nice clean face that way. And this is definitely a skill. If you're doing lots of cross sections on the plasma PFIB, you need to practice this, because it is tricky to get really tall cross sections and to get them to be smooth without using this this technique. All right, so let's go back to doing the TEM lift out. And for the TEM lift out, the next step is going to be to do the undercut. So we want to remove the material here on the left side, here on the right side, and across the bottom. And we want to leave ourselves a little bit of like a bridge or a little connecting tab so that the thing doesn't fall into the pit. But we want to cut away all of this stuff right here. Probably want to be at still a higher beam current for this so it doesn't take forever. I'll leave it at 15 nanoamps and we'll see what happens. But you know, feel free to do this cut at the higher. You could do it at 60 nanoamps if you really wanted to. Nothing wrong with that. This is still a pretty thick lift out too, so there's plenty of material there. All right, well, to do this cut, we're going to go to 0-degree tilt. And that, by going to 0, that's going to cause the fib to come in on a fairly shallow angle, which will allow me to do the undercut from the side. All right, we'll take a snapshot with the fib. And okay, there's the side view now of the sample by fib. I'm going to beam shift that to the center. And I'm going to just trust that my focus is still reasonable. This looks kind of blurry. Well, actually, no, it looks blurrier than I think. Let's I think it should. Let's try a reduced area window. Let's see if we can get this a little bit nicer. Since I've got that nice hole right there to focus on. For the really big beam currents, you can just sort of go with whatever the fib looks like. But as you get smaller and smaller, it becomes more necessary to actually adjust your focus. So what I want to do is I want to make 3 rectangle cuts. One rectangle cut here, one rectangle cut here, one rectangle cut here. So I choose a rectangle pattern, and I'm just going to go ahead and draw my first shape here. And I'm going to draw my second shape across the bottom of the trench, like this. And then I'll draw my third shape right like this. The spot where most users get into trouble is they don't know where to put this horizontal cut. If you put this cut all the way down at the bottom of the pit, as far down as you can see, most likely you're not going to get the sample to actually come free. And the reason for that is, let me pull up like paintbrush or something. It's just called paint now. Oh, come on. Why are you doing like that? Here we go. So if we look at the side view of our sample, we've got our surface like this, and we've built this platinum carbon deposition on there. And I've taken the fib and I've now excavated out the material like this, and I've excavated out the material like this. So all this stuff is removed. Right. This is all gone. Color that in a little bit. So what I'm trying to do is use the fib to cut on an angle like this from the side, and I want to cut underneath the bottom of this. And on my fib image, I can see from this point right here, let me change my color, right? I can see from here down to here, I can see that whole sidewall, right? If we go back and look at the fib, right? I can see that's from here to here. That's that whole view. But if I put my pattern all the way down here at the bottom of the pit, right? So that pattern would be from like, it'd be basically from like here to here. So that's my rectangle pattern if I set it in the bottom of the pit. What will happen is when I cut, is I'll end up cutting at an angle like this. And most of the time, you'll miss this back corner, and you won't actually get the sample to come free. It'll still be attached by a little piece right here. So you really want to, unless you know that the cut on this side is like really deep, right? Say this is cut down, considerably deeper on this side than this side. You don't want to put your pattern at the bottom of the pit. What we want is we want to make sure that that cut on this angle actually comes out, like right here. And if you extend these lines back this way, what you'll find is that where your pattern placement should be is somewhere around halfway between this edge and this edge to maybe about 2/3. So even though it looks like you're going to be throwing away a big part of your lift out, you actually won't, because when we thin this thing down, right, our final TEM sample is going to end up in the middle, this center line of this, and it's going to be taller than it appears to be from this cut. But avoid that temptation to put that pattern right down right here, because it usually doesn't work out. So what I recommend you do is look at, here's the edge defined by your platinum. This is the original top surface right here. Here's as far as I can see. Split that up into thirds and put your pattern about 2/3 of the way down. And I find that it works out pretty well usually. So this would be, like 0, here's 1/3, here's 2/3, here's 3/3. So go at about 2/3, I would say right about there, and we'll see how this goes. And then we'll adjust our side patterns accordingly. Make sure you leave a little bit of a tab right here, otherwise, this thing will fall into the hole after you cut it free. And try not to make these cuts super narrow. You want them at least a micron or two wide. If you make the cuts too narrow, you get a lot of redeposition problems in those trenches, and it's likely that this thing will get stuck. So you'll just make it harder on yourself. The last thing we want to look at is we want to cut all 3 of these rectangles at the same time, and to do that, we have to go up here into the pattern control and set it from serial mode to parallel mode. And we just click on this little icon. It's like a little electrical circuit, and we say confirm. So now we're running in parallel milling mode. I don't know what value to tell you to use for Z. You're going to watch this in the live view, and you can actually see when it cuts through all the way. So what I would recommend you do is just select all 3 patterns and set it to be some like big number. It really doesn't matter. We're going to stop it manually anyway. So let's go to full screen so we can see it a little bit better. And we're going to hit play. And then I would recommend you adjust your contrast and brightness a little bit so you can see some features down in here. So as this is cutting, as the fib breaks through, you should generate little like dark spots, which will be the evidence that there's a hole there. And depending on the beam you're using and how well it's focused and things like that, it might be a little awkward to see it, but generally you just want like a lot of contrast. So like this black spot right here and this black spot right here, I think are the holes in the corners. And what we should see is those expand and kind of go across the whole bottom of the trench. We also are looking for the sides to disappear, but almost every time I've ever done this, the bottom is the last part to come free. So usually these, you don't have to really worry about the left and right side. It's this part right here that's going to get you into trouble usually. All right, so for sure, this little dark spot right here is a hole. And if I pause my fib cut for a second, if we go look at the SEM image, we should see some evidence there that we're breaking through. And you can see kind of right down here on the sidewall, there's that hole punching through in the bottom corner, and it's kind of leaving a mark right there. And you can see we're about 2/3 of the way, maybe a little more than that, cut through right there. And here's the hole in the other corner right there coming through as well. So we're making progress. We're not quite done yet. So we'll go back and just keep cutting. But again, what we're looking for is we want to see these two black holes in the corners. They need to come together across this entire bottom in order to know that the lift out is free and it's going to actually be able to be picked up. And just based on how long this is taking now, I'm kind of wishing I did this at the 60 nanoamps instead of the 15. I think you always want to use the highest beam current you feel comfortable with, and just because it saves you time, and time is money. But at this point, since I've got it set up, I think we'll just let it finish here. But it might take another minute or two for this to complete. All right, so we're getting close here. You can start to see the edge is starting to be formed right here. That's kind of this white contrast. All right, there, the edge, that gap is expanding enough that it's starting to turn black now. So this is an edge going through here, but it's still connected over here on the right-hand side. So we want to wait for this to go all the way across. And you definitely have to be patient because these little, like this little corner right here, if you stop it early and that's not free, that will prevent you from being able to pick this sample up successfully. It'll break off every time. So make sure everything is clear. You know, even if you got to let it cut for another minute, you don't want to lose your sample at this point because you probably got at least an hour into the process so far. And as I said, the left side and the right side are going to be cut free almost every time by the time the bottom's cut. All right, that looks pretty good. I can see the black contrast going all the way across. So I'm going to go ahead and hit stop, and we'll just double check with the SEM real quick, see what that looks like. And I can tell that that kind of J shape, I can see it cut into the sidewall going all the way around here. So I know that this is free and it's good to go. As the beam goes through and cuts the sample, as the beam hits this back wall, it does have a tendency to sputter away this material, and that'll build up on this back face of your lift out. And you get these little like corners that grow out. These can actually grow out so far that they'll make contact with this wall, here and here especially, and that'll cause you problems. You won't be able to pick up the sample. If you're getting that kind of issue, or you just want this to look cleaner, what we do is just tilt back to 52 degrees with the FIB and do a quick little rectangle cut to sputter away this front face, and that will solve that problem. So just to show you what that looks like, we're just going to go back to 52 degrees on the stage tilt. And I don't need to change my FIB beam current. The 15 nanoamps is fine for this. All right, you can see here on my SEM image that the side is all covered up with junk now, right? We can't really see any of that grain structure anymore because it's all coated with that redeposition material. So on our fib, we just take a snapshot. I'm going to place a rectangle pattern, just kind of like right here, and hit go. And this only takes, I don't know, 5-10 seconds. It doesn't take very long to clean up that face. The redeposited material is usually amorphous, and it's pretty soft. It usually cuts pretty fast, even if your other material was fairly hard. So you see here that just in like 10 seconds, I've removed those little wings. So the bottom of the lift out is nice and square again. And you can kind of see the grain structure is back. There's still some junk on that surface. It's not totally cleaned up, but it doesn't really matter. We're going to put this on a TEM grid and thin it out over there, so it doesn't have to be perfect right now. All right, so now we're ready to do the lift out. We're going to go back to 0 degree tilt with the stage. Now, I mentioned way back when we started, I haven't used this tool in a while. I have absolutely no idea right now if the easylift needle is good or bad. It could be bent, it could be missing, I don't know. I also don't know anything about the calibration. So when you come in to use a system and you don't have, in this situation, it's probably not a wise idea to just go over here to the easylift control and say insert. Because if the last user left the needle in a really weird state, the needle could come in and poke this thing and wreck your sample and wreck your lift out, and now you got to start over again. So what we want to do, let's drop our fib current down a little bit so we can see what we're doing. We're going to move the sample well out of the way, and we're going to put the easylift in, and we're just going to check and make sure that the status of the needle is good. That way we don't risk wrecking our sample. So I'm also, while I'm doing that, I'm kind of setting up the tool for doing the lift out. And what we want to do is zero out the beam shifts on the SEM and the FIB. So I zeroed out my SEM beam shift, and I put the lift out right in the center of the SEM. And then I'm going to do the same thing with the FIB. And my aperture is stuck again. So I lost my image. So what we're going to do is we got to play this game, go back and forth with the beam currents until I get my aperture back. Okay, there we got our image kind of back. So if I zero out my my beam shift on my fib, you can see that when we're at 0 tilt, the sample is not in the center line of the fib. And normally you want to be at the eccentric height, but when you're going to do a lift out, you don't want to be at eccentric. You want to be at the coincident point between the two beams. So I already know my sample is right beneath the SEM. So what I want to do is I want to change the height of the stage so that the sample is right underneath the fib without any beam shift. So just like this, right? So SEM, it's underneath the center of the SEM, no beam shift. Underneath the center of the fib, also no beam shift. And this is the position, let's remove all these saved positions. I'm gonna add, and this is where we're gonna do the lift out. So again, it's not exactly at the eccentric height. On a perfect tool, it would be the eccentric height, but this one is obviously a little bit off in terms of the mechanical calibration on stage. So what we want to do is we want to get it well away from this sample. I find because we have the navcam image, the easiest way to do is just click over here somewhere in the open space around the sample. It doesn't really matter how far you go. Just make sure there's nothing underneath the lens. And what we're going to do now is go to our easylift control, and we're just going to say insert to park. Oh, yay, look at that. The needle's all screwed up. So it looks like someone ran the needle into a sample and has mangled it pretty good. We could, in theory, cut this with the fib, but it's probably not worth the time to do that. So I guess as part of this training, we're going to change the easylift needle. And if I look at it with the fib, it's probably going to look equally disgusting. yeah, this is pretty pretty screwed up. So let's go ahead and we're going to change the easylift needle. Actually, that's a good thing because I don't have my TEM grid in the chamber right now. If you notice, I only have my bulk sample. Um, so what we need to do is to put in the TEM grid as well. I was hoping to do the lift out and then take this out because this is a little bit magnetic, but I guess we'll just have the TEM grid in at the same time, and we won't be able to use the high resolution lens mode, but that's okay. So the procedure for changing the easylift needle is first let's take out the needle. We'll retract it. We're going to go to the alignment panel, and we're going to choose alignments for easylift, and we're going to run the easylift needle exchange and calibration. And on this software, it's really nice. It walks you through all of the steps, so you just sort of like follow the procedure here. And it says no samples necessary. That's just because you only need the SEM and the FIB beam, but we're going to have our samples in there anyway. So we're going to say next. And the first step is to vent the chamber and actually change the needle. Now, it is possible that the needle calibration gets messed up, and in that case, you can skip the vent and pump cycle, and you just click next, and you can move on to aligning the needle. But in this case, we actually need to change the needle out. So we're going to hit vent chamber, and now we'll turn off the beams, and it'll start the chamber vent, and that'll take a couple of minutes for this tool to vent. Now, while that's venting, I'm going to take a break for a minute, but we'll get set up. I have one webcam in here. It's probably not going to be the best camera to show how to do this, but I'll try to position it so that you can see the procedure. But we might have to go through the training again in person if you're not clear on how to do this. So the chamber's venting right now, and I will be back in a couple minutes. Okay, I'm back, and let's turn on the webcam. Okay, so what we gotta do, I gotta move my computer cart here a little bit. Okay, so the chamber is vented. You see I can pull the door open, and we'll go ahead and change the easylift needle. And to the first step is we need to get the alignment tool from the counter. So it should be sitting by the microscope or on the work table. In this case, it's on the work table, so over here on that bench. And the tool that we're looking for is this guy. So this is just a big piece of aluminum. You know, I wouldn't drop it on the floor or anything, but there's nothing fragile on it. And it has 2 pins on it, 1 pin right here, and 1 pin right there. And the way this works is we're going to open up the cover on the easylift door. And I just realized my camera should be on the other side. Let's move the camera here. Actually, I wonder if I can get the camera up higher. Maybe I'll just hold the camera by hand. Maybe that'll work. Okay, so the cover on the top of the easylift, this just swings open. So we just pivot that open. And this is the easylift shaft and motor assembly for the rotation motor. And this has to be removed first. And all we're going to do is just grab onto it and just pull until it comes loose. And you're just trying to unhook the electrical connector. So now it's loose. You see I can slide it in and out very easily. Don't pull it out just yet. Just get it loose. And now I got to put the webcam back because I need both hands to do this. But what we're going to do is I'm going to pull this out about this far. And then that probe, the shaft guide, this part here, those 2 little pins lock into 2 corresponding dovetails down inside there. So you drop the pins in like that, and then this gets tipped up and it'll click into position. And it gets held by 2 little spring like ball bearing detents. So let me see if I can get the camera to show this a little bit nicer. Get this up as tall as we can go here. Actually, that's not too bad. Okay, so again, I got 1 hand on the guide, 1 hand on the probe shaft. So I'm going to pull this out a little bit. I'm going to take the guide and set this in here on those pins, and it'll catch. So they're little hooks. So I hook that in, and then what I have to do is I have to raise this up enough that. Hold on, let me get the camera so you can see what's going on here. You see how this is bumping into the housing on the probe shaft? So I need to raise it up enough that can clear, and it'll click up into position like that. And now you can kind of let go of it. Be really careful not to pull down on this because this doesn't stay in position with a whole lot of force. And what will happen is if you pull down on it, it'll unlock and it'll drop. And especially on the older, like the G3 easy lifts, this would actually, it had a tendency to fall out and it would tumble down onto the counter. And it's kind of a mark of shame, but on any of the Generation 3 tools, if you look down here on this counter, I guarantee you on almost all of them, there's always a big ding right here from someone dropping this easylift guide, and it'll fall down and it hits that surface and it puts a big gouge in the counter. So just try not to let that happen, because it does mark up the tool. So again, you pull that out, put the guide in, lock it in place, tip it up until it locks. Now at this point, the guide is just there to help you pull the shaft out straight without banging the needle into anything. But to be honest, the needle is wrecked already anyway, so it doesn't really matter if we hit something with it. But especially when you go to put the new needle in, you definitely need this guide in. So we just carefully slide this out, and I just kind of keep the probe shaft in contact with the guide as I come out. And here's our probe. Now the probe, this is the whole rotation assembly for the easylift. So if you look on the end here, there is actually a little mechanical knob that you can do rotation with, but the rotation motor's in there as well. The whole probe shaft needs to be kept clean, so don't touch this unless you have clean gloves on. There's a couple O-rings on here that, it's a good idea to look at them, make sure that there's no like big dust particles or anything stuck to them. And then down here is the little spring mechanism that actually holds on to the needle, and that's how we're going to change the needle out. So let's go over to the counter, and hopefully I can get this to show for you, and you can see what we're going to do. Okay. All right, so the alignment guide that you need is this device right here. So just pick this up and set it on the counter. All this is it's a little two set of V blocks. So you got a V block here and a V block here. And then there's a little magnifying lens and an alignment stripe down here. What we want to do is set the probe shaft on those V blocks, but you need to do it so that this little collar, it's not focusing. But anyway, that little collar just next to the O-ring, there's like a hard metal 90-degree edge right there. That edge needs to go in contact with the left side of this V block. And I'll try to show that here. All right, so you can kind of see here. This is the correct way to do this, so that you can freely spin it. It slides, and you want that edge. You want that metal right up against that aluminum. Unfortunately, what's really easy to do is to accidentally set this up like this, so it's resting on that O-ring or on this thicker collar. And what that'll do, if this is the problem, is over on this side where the easylift needle is, that needle will be going on a downhill angle, and it'll run your probe into that surface, and it wrecks the needle every time. So make sure that you have this sitting on the right surface back here on this side. Otherwise, the probe shaft will not be level, and it'll bump the needle down over there on that end. That'll run into the that alignment surface. The other thing is, if you notice here, the probe shaft housing has like a curvy side to it and a flat side. You have to have the flat side up. So if you set this on here with the curvy side up, again, it won't even sit on the V block. And over on the right-hand side, over here, this will just be going downhill and running into that surface, and it will break your needle off, and bad things will happen. So curvy side goes down. Make sure you're right up against that shoulder. And again, also make sure that even if you're sitting on this correct surface, make sure it's pushed all the way to the right so it's metal on metal. That's really important. All right, so now what we're going to do is we're going to come back over to the other side, and we're going to look at the needle. And again, I don't really have a good way to show this, but you should be able to spin the probe shaft around with the hand control if you want to. And this OmniProbe needle is held in place just by a little spring. So right here, this is just a little leaf spring. Come on, focus. There's a little leaf spring right here, and I think I need to, let me see if I can get my focus to be manual. Let's see, properties, configure video, camera, focus. All right, I think that's about as good as it's going to get. All right, anyway, so we have, you can see the little leaf spring right there. To pull the needle out, just grab a pair of tweezers. It doesn't really matter how sharp they are. And you're just going to grab onto the needle and just pull it to the right until it comes loose. And then this is our garbage needle. You can just throw it away. We do have a exchange kit that has a sharps disposal box in it, as well as the tweezers and the new needles. So go ahead and grab that. Now we're going to take our new needle, and we're just going to grasp the needle, and the new one, and we're just going to slide it back into that spot. Be really careful that the new needle doesn't run into this surface right here. You don't want to break or bend the tip of the new probe. All right, so I got the new needle, and I'm just going to put it underneath that spring, slide it back, and then let it come down. Now, the last thing that's real important is we need to set this up so that the end of the easylift needle is right at this black to white transition. And there's a magnifying lens on here that's supposed to help you do this. And let's see if I can get this to show up. I'm probably not going to be able to show this on the camera, but if you do take the webcam, or if you're looking down over the top with the magnifying lens, it kind of helps you see down in there. And the idea is just slide that needle left or right a little bit so the point is right at that white to black line. So I'm going to go ahead and do that. That's pretty close. I'll show you what I'm looking at here. Right. Right. So the needle right there. Okay. So what we want to do now is, let's turn our autofocus back on. We want to carefully pick up the needle and when you pick up the probe shaft, and when you do that, pick it up so the right side comes up first. If you pick up the motor housing on the left, right? If you pick up this side first, that side will go downhill and it'll bump the needle into that surface. It'll wreck your needle. So we're just going to real carefully pick up the right side first, and then take this out, and then we're going to head back over to the microscope. Of course, I got to redo my tripod one-handed because I'm holding the probe shaft. I don't want to set it down. There we go. Okay, so at this point, we got to be a little more careful with our procedure because this this needle, if that touches anything, it's wrecked. So when we go back down into this hole, we need to make sure that we're in contact with this guide the whole time. Otherwise, our needle is garbage. So what I recommend you do is take the probe shaft, just kind of gently set it on the guide. Again, don't push down on it because this thing will unlock and it'll fall. So just real gently set it on there. Tip this uphill until it's about parallel with the guide, and then just let it slide down through the hole. And there's a little bump right here that you got to go over on the probe shaft, so just kind of let it ride up over that O-ring, and keep sliding, and then another bump right there. Now, once you get the motor housing is touching the guide rod, at this point, there's not really anything for that sharp needle inside the chamber to run into as long as you don't move this a lot. So what we're going to do is just hold on to the probe or the motor housing. We're going to drop the guide rod out and lift it out of the way. And then just carefully let the rest of the probe shaft drop down into the hole. All the way down. And now we just need to make sure it's plugged in. Don't forget this step. It's important. You've got to push it down until it clicks into place. Make sure it's all the way in there. If you don't get it pushed all the way down, you'll get all kinds of weird errors, and you won't be able to do the alignment of the easylift. And then just close the cap, and the easylift is now all good. So the last thing I got to do is I got to put in my TEM grid holder. This is going to be a similar process to what I showed in basic training. So I need to change out the stage adapter, and I need to put in my TEM grid. So if you bear with me here, we'll go ahead and do that. And I can show it on the video. I'll move the webcam so you can see what we're doing. So here's the side of the chamber. So roll open the door. I'm going to move that stage out a little bit so it's easier to get to. All right, so go ahead and loosen the locking cone nut. And spin this around a little bit. Okay, and we'll take out the, I can move the mic a little closer, I guess. Take out the stage adapter. Oop, drop the stage adapter. Okay, there it is. And we'll just set that aside, and then I'm going to put in the crosshair holder that holds 5 samples at a time. All right, now we'll put bulk sample back on. Lock that down. And then my TEM grid. So here's my TEM grid holder. I'm using these TEM grid holders. They're made by OmniProbe. They're kind of pricey, but they're real nice. They're low profile. They hold onto the grids real well. So I highly recommend these, but they're about $1,000. So, which in the grand scheme of these tools is not that expensive, and they last for just about forever. But they are a little bit on the pricey side if you don't have one. So we'll go ahead and lock that in. And then, very important, remember to use the height gauge. We want to check our height. And that looks good. We're a little bit on the tall side, actually. Let's go a little bit shorter. I want the gauge to just barely touch the side of my sample so as I come over. That looks good. That looks pretty good. All right, let's go ahead and lock it down. Get on with our training here. All right, everything's secure. Give it a little wiggle test. And then I'm watching the CCD camera as I push the door closed. Okay. And we'll go hit pump. So now we just have to wait for this chamber to pump back down, and then we can proceed with aligning the easylift needle. So that'll be a couple minutes. So it looks like we're almost pumped down with the vacuum. I'm going to go ahead and move the stage a little bit. We'll go back and find our lift out site. I can delete this save position because this is from the previous holder, so that's not valid anymore. Takes a little while to pump the chamber down when I had it vented for so long. Usually better to vent it, change your sample, and pump it down. But going through all that explanation about realigning the easylift needle is makes it a little slower to pump. Okay, pump down. So let's turn on our beams. And we'll have to find our lift out site, which fortunately I think it's right there. So again, find the site. We want to focus on it. Link our working distance, and then we're going to go to 4 millimeters. Put it in the center again. Focus, link again, 4 millimeters, and then we'll use the align feature tool to get that lined up again. We'll make it horizontal. Oops, I went the wrong way, so we need to do a relative 180-degree rotation. Okay, and let's double check with our FIB that our height is the correct height. Yep, we're a little bit off on our height. So we want to go and drop that down just a little bit. And we'll save this position. So just like before, get away from the sample. Let's get out here over here into like kind of no man's land. And we'll go back to our easylift alignment. So we already did the vent chamber, we changed the needle, and we already did the pump chamber, so we don't really need to hit this button to pump it down. So we're just gonna go ahead and hit next. for safety, the software, the wizard here will drop your stage down by 6 millimeters, or to 6 millimeters, and that's fine. So now we just sort of follow the steps. So step 4 says calibrate, push the button. This is, I don't know why they said calibrate. Really what they're doing is homing the easylift axes. So just push calibrate. It takes a few seconds. And when it's all done, it should insert the easylift needle. Okay, there's the needle. So now we hit next. And now what we need to do is we need to move the needle to the center of the SEM image and also to the center of the FIB image. And they give you these little cartoony things to kind of show you what you're doing. So we're going to click and we're going to move the SEM image first. And I'm just going to use the overlay, which I didn't really talk about this yet, but we just sort of click and drag with the mouse and that will move the needle around. In X and Y, and if we go over here to the FIB image, we can click on the right here where it says jog Z, and that will allow us to move the needle either up or down and get it into the center of the FIB screen. Usually you have to do this a couple times, back and forth between the SEM and FIB. We'll get it lined up on the SEM. FIB, and so on, back and forth a few times. Close enough. All right, now we hit next, and the needle's going to rotate 90 degrees, and then we have to bring the needle back to the center. And unfortunately, there's no overlay for this one. You have to use these up, down, left, right buttons. But we just want to click the needle back to the center, and you can change the step size as you go here. And just bring it back to the middle. You won't probably be able to get it perfect, but this is close enough. So we'll say next, and then we want to click Save Alignment. And then we can click Finish. And then the stage will go back to where we were. Okay. Now you notice the stage went back to where we were when we vented the chamber. So I guess be a little cautious about that. I forgot about that behavior because normally you wouldn't be changing the adapter out while you also do the easylift needle. But fortunately, I saved my position, so I'm going to double click on position 1. That'll take us back over to the lift out site, and now we can actually do the lift out. So to use the easylift needle, we're going to go click on the easylift tab, and we have an insert button, and there's 2 saved positions. There's a park position and eccentric point. The eccentric point will put the needle like right here in the center of the FIB and SEM screen, so that would cause the needle to crash. The park position is directly above this spot by 200 microns. When I click insert, it's going to ask you, do you want to simply insert the needle or do you want to go to park? I would recommend you go to park because if you click insert, the needle goes to wherever the last position was, which who knows where that is. It might crash. So we're just going to say go to park. And the needle should come in right above the sample. There it is. And if we were to measure that, I don't want to look with the FIB because I don't want to damage the rest of my surface, but that should be 200 microns above this point. Now to move the needle around, you have this easylift overlay that appears on the screen. If you click the mouse in this area of the screen, it lets you click and drag the needle in X and Y. If you click the mouse in the jog Z area to the right, it lets you go up and down in Z. And this overlay will move with the quad. So if I go over and click on the FIB quad, I now can move X and Y relative to the fib image and also the jog Z here. The rotations down here, these two buttons move you by fixed rotation steps. You can change all this by going over here. So the rotation step size can be changed by changing this number in the easylift control. You can also have additional rotation buttons here and here, or you can go directly to a certain rotation coordinate by typing in right here. If you're used to running OmniProbe needles or the OmniProbe manipulator, you can also use this set of controls, which is very similar to the OmniProbe software. So you can run it in jog mode or step mode. In jog mode, this goes in fixed speed. So if I click to the right, it's going to move 10 microns a second right or left and so on. And then you got your Z up and down. If you put it into step mode, it will move a fixed distance every time you push the button. Be careful about this one because there's a 100 micron step, and that's a pretty big move. And especially if you hit the Z down button, 100 microns, you can plow that needle into the surface of your sample pretty easily. You can also save positions. So if I come down here and click add, I can add positions or remove them for the easylift. The park and eccentric are always going to be there. So if I click on park and say go to, it'll take me back to park. What I like to do if you don't want to zoom out to see the probe is, I know because I just aligned the probe, it's 200 microns above the sample. And I can use these step modes over here to kind of bring the needle down a fixed distance. Now, unfortunately, there's only the 100 and the 10 micron step. So if I do 100 micron step down twice, I'll crash the needle. So what I like to do is go 10 microns, and I'm going to go 10 microns up. 1, 2 clicks up. So now the needle should be 220 microns above the surface. And then I can go to the 100 micron, and I can go down 1, down 2. And I'm going to take it off of step mode so I don't do something dumb. And if I go look here, we should see that the probe is now 20 microns above the center line of the fib image, which is pretty close right now. So there I can see the probe. At this point, I can use the overlays to move it around. So I'm going to put the needle over here to the left-hand side. And then I'll use the jog Z, and I can bring the probe down into that gap to the left of the sample. This is where I would try to attach it. Now, to weld the probe to the sample, we need the gas injector. So let's go over to the patterning tab, and we're going to insert the multichem. And that'll allow us to deposit material and weld the probe to the side of the sample. Now, for this weld, I'm going to use 30 kV. I mentioned you get bubbles in your deposition at 30 kV, but for this, I don't really care. I'm not going to cut through it. It's just to attach the needle to the side of the sample. So let's just double check that my needle alignment looks good. I've got it right on the left side of my lift out, right in the center line. And if I go and look with my fib image, I'm a little bit too high. So let's bring the needle down. And then I'm going to carefully move the needle to the right until it just touches right there and back up just a little bit. You don't have to be touching the sample. It's actually better if you're not. Just a little tiny gap is good. So what we're going to do now is fill in this area with the deposition of choice, either platinum or carbon. I'm going to use carbon. So I'm going to take my pattern, and I'll draw a little rectangle pattern right here. Just like that. And I'm going to change my application to be carbon MC2. And in terms of depth, it doesn't really matter. You're only going to run this for about 30 seconds. And I'm going to hit play. And if we look in our real-time monitor, we should see that this kind of fills up with carbon fairly quickly. Oh, I forgot to mention, check your beam currents. Right, we're at 100 picoamps, which for carbon depth, that's okay. But if you're going to do this with the platinum, you're going to want to drop your beam current down to the next one down, which is 30 picoamps. If your beam current's too high, this just won't deposit very well. All right, that looks kind of, I can see it's kind of blobby, so that should be good. We'll stop our deposition. And now what I want to do is bring my pattern over to this side, and we're going to cut off with the silicon application file. And I need more beam current for this cut. So let's go up to, say, like the 4 nanoamp. This should be good. Hopefully I don't have to play games with the apertures this time. See if I get about 4 nanoamps of beam current. And I'm not, so I don't think I have a beam. Oh, yeah, I do. Okay. So we're just going to do a thin little rectangle pattern right here to cut that off and hit, let's set our Z size to be some big number and hit play. And that, at this beam current with such a small pattern, that should cut pretty quick, maybe 10 seconds. And I can't really see that well with the FIB, but I think it's cut, so we'll look with the SEM, and sure enough, it looks like it is cut free. If you're not sure, one of the good things to do to test this is take your hand and just tap on the side of the microscope table a little bit. Just gently tap on it, and if you see the sample and the probe shake together like this, then you know that the sample is not connected to the substrate anymore. So now what we're going to do, we'll drop our FIB current back down to a smaller value, and we're going to carefully work the sample out of the pit. Now, my mouse, right now I can't use my easylift overlay because my mouse is this pattern crosshair. So again, I have to go back up here in the toolbar and I select the mouse pointer to get my mouse control back. Now, I'm pretty sure if I just go straight up in Z, I'm going to run into this, this tab. So what I'm going to do is I'm going to go to the left a little bit, and then I'm going to go jog Z up, and I'm going to try to get out of the hole that way. That looks pretty good. Once I'm away from the surface of the sample, let's just get up away from the surface a little bit. And now I'm going to send this back to park. So I'm going to click, double click on park, and that moves it to park. And then I can click retract. So now we're ready to go over to the TEM grid. So I'm going to take out the multichem. And then we'll use the nav cam image to head over to where the copper grid is, which I think is this position right here. Sometimes it's hard to, yep, got it right. Sometimes it's hard to see the grid in the nav cam image. All right, so new sample. First thing I always have to do is focus. So focus on the top of that grid finger and update my link and go to 4 millimeters. And then we're going to use our XT or align feature tool to make the grid parallel to the screen. Now, this particular grid has 4 fingers on it. I'm going to attach my sample to the left side of one of these middle fingers, and there's some topography, or there's some thickness here, and you usually want to have your sample kind of in the center line of the TEM grid. That way, if this grid falls on the table, your sample doesn't get busted off quite as easily. If there's a lot of curvature right here, you may find that you need to look for like the widest area. So like I may attach the sample like more like right here, just because if I attach back here in the center line of the grid, I kind of lose some of my lift out because it'll be shadowed behind this curve. So right here is good. I mean, I still have 30 or 40 microns of the grid protecting the sample right here. That should be okay. Now I could tilt the stage and find the eccentric height of doing this, but the easier way to set the height with the TEM grids, because there's no sample on here to damage, is just look at it with the FIB. And what I would do is just adjust the height of the stage so that wherever you're going to attach the sample is right in the center of the FIB image. So I'm going to attach kind of the side of this finger right here, just like that. So that looks pretty good here. I'm all set. So let's go to the easylift, and we're going to say insert to park. There's my lift out, and here's the lift out 200 microns above the center line. So I need to move my sample to the left, so I'm going to use the mouse overlay, go left, and then I'm going to go jog Z down and bring this sample right next to where I want to attach it. Let's go ahead and bring in the multichem. So we go back to patterning. We're going to insert the multichem. There's the multichem needle. And now we want to bring that sample right up next to the side of the grid where I want to attach it. So we use the SEM, kind of get it centered in the up and down direction. Bring it close. And then we'll go to the FIB image and we'll do some fine adjustment of the position here. So that looks good on the FIB image. That looks good on the SEM image. So now what I want to do is carefully bring this to the right until it just touches that copper grid. It can be a little hard to see when it touches. You might see this deflect a little bit. You might see a contrast change. Right there, see it's kind of sliding up and down a little bit, so let's back up just a little bit. Just go nice and slow until you think it's touching. That should be good. And now we want to fill in this gap with the carbon or platinum, up to you. We're going to need a little more beam current for this. I'm going to jump up to the 0.3 nanoamp, and I'm just going to use carbon to fill in that spot. So select the rectangle pattern, fill in all of that, and we're going to do the carbon M and hit, and we'll do a 0.5 micron and hit play. Now, once you think that the sample is attached to the grid, go ahead and stop the deposition and cut the easylift needle free. We don't want to have any accidents, and if this thing is not stable, if it drifts, we don't want to have one of these welds break, because if this weld breaks, we could lose the sample. So once you think it's actually attached, cut this free, and then you can go back and add more carbon or platinum later. But it's always dangerous to have the easylift welded to the stage, which is what we have right now. So just be careful about that. And we can kind of see here, this gap will kind of close up as the carbon builds up in there. So I only have about 20 minutes left on this FIB session. I'm going to do my best to get this sample thinned in 20 minutes, but it's going to be a little bit of a rush. So if I don't finish, I am going to have to sign off the tool at 2. And we hopefully you'll be able to figure out how to finish the samples on your own, but if not, we can do another training to go back and finish this. But I'm going to go pretty fast in terms of the thinning operation. All right, this has still got a little bit of gap right here, but I think it's attached. This part up here looks solid. So I'm going to hit stop, and I'm going to go, see, this is where we're at, and we're getting some drift, and this is what I was afraid of. got to watch out for that. Probably can't fix this now, but if this happens really early on the weld, you can try to move the probe a little bit and like straighten that out. But more likely, what's going to happen is it's going to break and fall off, like I think it almost just did there. So right now, I probably just broke the weld off between the sample and the grid. So I definitely need to do a little bit more of a deposition there. Otherwise, I'm going to have problems. So we'll get that stuck back down again. And then I'm going to go cut this off. And that should be good enough to hold it. All right, so let's change our application file to a cutting file, and we'll slide this over here. And we're just going to do a thin little cut. It doesn't take much to do this. I hit play. One nice tool is if you can't really see in that pattern because it's so small, you can use this little magnifying lens in the, where is it? It's in the pattern control, right here, this little magnifying lens. It zooms into your active pattern. Maybe a little bit too zoomed in, but then you can kind of see what's going on in there. You can also use the digital zoom function, manually control that. Oh, there, it just broke free. So, uh-oh, we got some problems going on here. All right, so fixing a grid at this point is risky, and I think I should have done a little bit more carbon. What we can do is try to straighten that out, but it's a risky venture. I'm going to use platinum just because it'll deposit quicker. And what I'm going to do is I'm going to move this probe over this way. I'm going to reattach it. Of course, now I lose my FIB current. Okay, so again, this is kind of a dangerous maneuver. What I'm going to try is I'm going to try to fix this, get it straightened out. And what we need to do is first get it back attached to the easylift. So we're going to do a little platinum deposition right there. PTM. I'm looking at it live with my SEM. And once the easylift is connected, I'm going to use it to try to straighten this guy out. Just real careful. All right, and now what we want to try to do is to fill this back in with platinum, either carbon or platinum. I guess we'll just use platinum since it builds up pretty fast. But so not ideal. Never fun when that happens. The easylift control does let you, have a little bit of chance of saving that. I don't know why it turned so much when I cut it free.
Is there a need to like realign it? What if it's a little like distorted? Does that matter much?
It doesn't matter that much, especially so in this view, if it's like rotated this way, it doesn't matter at all. Because in a TEM doesn't care this sort of rotation alignment. What really hurts though is in like the SEM image, if it looks like it's tilted differently, or like say it's going this way on the SEM image, that means when you put it in your TEM holder, you're going to be way off in terms of your alignment. So if this lift out was done according to some like specific direction, and then you're really far off.
Got it.
So I don't know why it's having so much trouble here. Usually I don't have this problem, but I think let's just again, I don't care about that alignment as long as it doesn't look. I mean, it's pretty straight with the grid here, close enough that I'm not too worried about that. So let's just get it cut off, and we can weld the other side, and we'll move on with what we're doing here. And I don't know if it's drift or if there's like a something in the weld is not behaving. I'll go ahead and cut that off. All right, so it's cut free. It did turn a little bit. I don't know, maybe using carbon was a bad idea. Maybe the carbon is causing it to pull a little bit. But so the probe's free, and we're going to send the probe back to its park position and retract it. And then I want to weld the other side of this just to make sure that this doesn't fall off. Now to weld the other side, I got to rotate this around. You can actually speed up the deposition quite a bit. Instead of rotating 180 degrees, I'm going to rotate 135. So I'm going to do a relative 135 rotation. And what that'll allow me to do is I can get a much faster deposition from the multichem this way. Because now that the fib is like pointing into this corner, and the multichem is pointing right in there as well, so it just tends to grow faster. Instead of going all the way around to make it horizontal. So we'll do the carbon M again, and we'll fill up this side as well. And something like half a micron should be good. So I do have on my personal, if you search out my YouTube channel that I made, it's not part of the MC Squared channel, but I do have another video where I did a TEM lift out on a silicon sample on the PFIB, and that one I didn't have these weird issues. So if you want to watch another video of another example of doing this where I didn't have to struggle, that one's out there. So once this is welded, the thinning procedure for TEM samples is going to use the cleaning cross sections, and we're going to use probably the 15 nanoamp beam current to try to thin this chunk down to get it to around, I would say, about a micron thick, maybe half a micron thick, and then we'll start dropping the beam current down and doing more controlled cuts to bring the sample down to electron transparency. And once we get it to around 200 nanometers thick, we're then going to drop the voltage on the FIB and do like a final polishing step. So let's see if we got some carbon building up on that side. Yeah, we'll go a little bit more there just to make sure. That's probably safe. It doesn't take a whole lot to hold these things onto these grids, as long as you don't poke them with tweezers or something like that when you're handling them. All right, so let's align to the, I'm going to align to the TEM grid. Even though my sample is off a little bit, when this goes into the TEM, or whatever I'm doing with it, I'm going to be aligning to the grid, not to this. So I have a thick enough sample, I can kind of fix this. But I can cut it square again, and it'll just be a little bit off from my original angle. So we're going to tilt to 52 degrees. And actually, we're going to have to tilt a little bit past 52. So whenever you're doing these thinning operations, you always have to add a little bit of tilt to your cut. And the reason for that is the FIB will not cut this side parallel. It'll always have a bit of a taper to it. You could kind of see it there in the FIB image before I close that image. And for things like steel, we usually need about 2 extra degrees of tilt. Now what I'm doing is I'm playing around with the position of the sample. I want to get it right underneath the SEM and underneath the FIB with minimal beam shift. Okay. So here's my sample. I'm at 52 degree tilt right now. I'm going to go to 54 degrees. So by adding 2 degrees onto my tilt angle, now I can cut this bottom side, and I should get a much more parallel cut. And let's go up to the higher beam current. Let's go up to 15 nanoamps. And I got to be quick on focusing here because I don't have a lot to work with, and I don't want to damage my sample. So when I change my beam here, I just got to be quick about focus and astigmatism. And then we'll use a cleaning cross-section pattern right along the side here. And we'll do that same 30 micron cut I did earlier. That seemed to work pretty well. let's hit go. When you're setting up your cuts, don't cut through your weld. That would be a bad mistake because the sample will fall off the grid. You know, also be aware of how big your beam is. So, you know, don't try to go too far into the center line of the sample if you're using a big beam current like this, because we don't want to sputter away the whole thing. And we can use the SEM with snapshots to kind of track what's going on. But as we saw earlier, if I take a snapshot, you might have a lot of you know, really bright contrast to deal with. So that can be a little frustrating. You can use higher beam currents on the SEM and things like that. I'm going to make my SEM snapshot a little bit slower. Let's do like 3 microseconds. Just to get a little bit prettier image here. So the FIB, because I'm using this big beam current, I'm getting a lot of these little like pillow type things, or pillars. These artifacts are really frustrating to deal with. They show up if your FIB is really badly focused, but they also show up just if you're using too high of a beam current for my cut. And the only really way to get rid of them is I can stop my cut and I can run this again. So I'm just going to basically repeat my cut as I come up onto the edge, and that should get rid of some of them. Or probably would be better would just be to drop my beam current when I go to clean up that face. And I think that's the approach I'm going to take here. So what I want to do now is cut the other side. So instead of going to 54 degrees, I'm going to go to 50 degrees. And now I'm going to come and cut, change my scan direction on my cleaning cross section. Instead of going bottom to top, I'm going to go top to bottom. And I'm going to get rid of this stuff. So once both of this cut's done, we should be looking at a sample on the order of, where's my pattern here, rectangle. I'm thinking somewhere around 1.5 microns, maybe a little smaller, but it's still pretty thick. And then I'll drop my beam current down and we'll keep cutting at it. But again, I'm going to have to stop here in a minute. I think there's another user coming on the PFIB right after here at 2. So I might have to finish this sample at some other time. Let's look at the schedule and see. Because, let's see, plasma FIB. All right, so there's no one at it right after 2, so we're going to try to finish it here in a couple minutes, and probably won't get a perfect sample out of it because I'm going to be rushed, but we can at least go through the basics of what needs to be done. So I can roughly assume that, I'm not looking at the other side of the sample, but I can assume that it's probably a similar quality to this side. So, if you need to see the other side, then instead of changing the tilt from 54 to 50, you'd stay at 54 degrees and you would do a 180 degree stage rotation. And that would allow you to see the side that you're cutting. That 180 degree rotation when you're at these tilts like that is a good way to bump into the lens cap. And that's really where this safe stage moves is really helpful. I'm going to go ahead and stop this because I think I'm getting to the point I want to drop my beam current. So let's drop down to 4 nanoamps. And I want to go back to my 54, and we'll cut on this front side again. See if we can get that to clean up. Check my focus. All right, so go back to bottom to top. And the smaller the beam current you use, the better the quality is going to be on this edge, but it starts to get kind of painfully long in terms of cutting time. So you see here, my time is now up to like 3-4 minutes or so. One thing I can do to kind of speed this up is instead of trying to cut through the whole sample now, I can just try to cut through like the top half of it, because I really don't need the whole thing to be the same thickness. So if I do something like this and then maybe change my Z size maybe down to like 15 microns, what this should do is it'll keep the bottom kind of nice and fat. Let's see what this looks like. Yeah, so I'm kind of only cutting about halfway down the sample now. And the smaller beam current, the hope is that it'll smooth out a little bit, and I won't have all these little artifacts on the face. I'm going to save this position because I think I'm going to rotate the stage after this to see what the other side looks like. While you're cutting, if you want, you can have the SEM take pictures for you automatically by using this feature called I Spy. It's in the patterning control. To use this, you just turn on the checkbox, and then you tell it how many of these cleaning cross-section cuts you want it to make before it takes a picture. So I'll just do every one, and then you just set your scan speed for your SEM. Let's do like 3 microseconds, and then unpause it. So now what will happen is, I'm starting to hammer my platinum, so I need to stop. When you're starting to lose your platinum, that's a big sign that you're going a little bit too far. But I didn't quite get that to smooth out, so I'm going to go back and recut this a second time. Maybe drop this down a little bit, maybe down to like 7. And you notice I'm not going to move the pattern. I'm going to leave it right where it is, just run it a second time. And that'll help kind of smooth out this junk on the side. Unfortunately, when you're doing this, these thinning steps toward the end are where it becomes less predictable, and it gets harder and harder to, for me to explain to you the exact sequence of steps that you have to follow to get a good quality sample. But so what I'm looking for is, I want to stop it. If I start to see this platinum cap start to shrink again, I'm going to stop it. But I'm trying to see if I can get rid of this this weird texture on the side. Yeah. All right. So I'm going to stop it and just run it again. So basically what I'm just doing is just keep starting and stopping it until I can get rid of that stuff. And I might not be able to. This is where the gallium fib and the PFIB are very different in terms of ease of use. The gallium fibs, you don't really have to worry about this stuff. You'll get a smooth cut pretty much no matter what you do. The other thing I might have to do is drop my beam current on the fib. I'm not really thrilled about that, but that might be necessary to get reasonable quality. try one more time and see. I think on this sample where I screwed up is I think I went too far with the 15 nanoamps. I think I should have left it a little thicker at that step. And then I wouldn't be fighting this these artifacts over here on the left-hand side. But I was in a rush, and I tried to do too much at the high beam current. So in order to get this left side looking okay, I'm probably going to end up wrecking the right side of this lift out over here. This is going to fall apart. But it's a 30 micron long bar, so I'm not super concerned about that. But it's not going to be uniformly great. So probably one more time should get this over here. But this is about the only way to get rid of these things when they start, is just to keep running the fib pattern over and over and over again and try. I'm not moving the pattern, so I'm trying not to thin it more. I'm just trying to get rid of this stuff. But unfortunately, because of the beam tails in the fib, it is still eroding this top a little bit every time it goes. I guess if I was only interested in like precipitation or some like small feature in here, there's probably plenty of real estate in the middle right here that this would be fine to just ignore this stuff on the left. And you can kind of see here that when you lose your platinum cap, that the texture on the side starts to go bad really fast, which is another thing with the PFIB. It's like if you lose your cap layer, you're in trouble. So. All right, I think I need to stop on this side because this isn't going to get much better than this. It's going to start to fall apart. So what I want to do now is I'm going to go over and check out the other side. So I'm going to save my stage position, and I'm going to turn on safe stage moves, because if I just do a 180-degree rotation, hopefully you can see here from the CCD camera that I'm going to bump into the lens, which would be bad. So I'm going to do a 180-degree. So with safe stage moves on, that'll drop stage, do the rotation, and then it'll come back up. All right, so here's my sample. All right, so they don't all turn out perfect. I guess that's one of the nice things about watching this live. You can see this one is going to be, I would say, like a B+ kind of quality, or worse when it's done. Yeah, okay, so yeah, this is getting pretty thin, and you see it's starting to curl up on me too. A lot of this buckling, it's either residual stress in the sample or it's fib damage on the surface. It causes some like compression and tensile stresses. And the only way to get rid of that is to drop your voltage down. So let me just get an idea of how thick this is. If I image my sample at a higher voltage, at some voltage, this will become electron transparent. And so we're at 3 kV, I can still see through it. Let's jump up to 5 kV and see what it looks like. So at 5 kV, you can see up here this platinum layer is really bright. That means that this part of the sample is electron transparent. The beam, the SEM is going through the sample, and it generates secondary electrons on both the front and the back, which is why it gets brighter. Whereas in the thicker areas, like over here and down here, it's still thick enough that you're only getting the secondary electrons from the front side. So if I jump up to 10 kV, let's see. I'm guessing it's probably, yeah, so like this area over here is thin enough to be transparent to a 10 kV electron beam. If you know your material really well, you can use this, like what voltage it becomes bright at, to be a pretty good judge of how thick it is. For steel samples like this, I would guess that maybe in this bright spot right here, it's probably on the order of like 200 nanometers. And over here, it's thicker. So this is still a pretty thick sample. What can I do to fix this? I can add a little bit more tilt. So instead of being at 54, maybe go to like 56. That might help get this thing to thin up without wrecking it. I'm also just going to worry about this kind of left side, or the right side. The left side over here is getting kind of wrecked anyway. So let's see if I can get this to be savable. Oop, starting to cut off half of that right there. All right, so this is going bad quick. I think we got to stop and go to the low voltage because I don't think it's going to get any better than this. So I'm going to drop down to 5 kV on the FIB. We can still stay at a pretty high beam current. That's okay. And we want to do our best to just get this in focus. And I'm just going to use a rectangle pattern on the side of this thing. Just like that. And this will hopefully straighten out again if I polish away some of that 30 kV FIB damage. At least that's the idea. So I'm going to hit play. And then let's watch it. Now I can watch it with iSpy, or actually with these lower voltages, you can actually watch them live if you care to. You just got a little bit of a scan noise in there, which if you use the averaging filter, you can get rid of a lot of that. So you can see it's starting to fall apart in there. Let's go a little bit higher tilt. Yeah, this sample's going bad real quick. But right in here is probably a good spot for TEM. Maybe in here is okay. That looks pretty flat. But I goofed this one up, I think. Let's go. We got to do a 5 kV cut on the other side. And we'll go back to that higher tilt angle. All right, so I wouldn't say this is a spectacular sample by any means, but it is what it is. To be honest, I haven't done a steel sample on the PFIB yet. This was the first one, but I think I should have cut it with more cuts at lower beam current, I think is what would have helped this one. Just to get an idea of where the thin spots are, let me turn my SEM back up to 10 kV. And so it does have, I mean, it's not a terrible sample. Again, if you were only looking for like a small area, probably all through here is pretty okay, but it's certainly not very uniformly thin. I've got a lot of these artifacts on this side and probably on the back side too. But in these these areas right here on this edge, it'll be real thin. It should do atomic resolution in there, just not a really wide area to look at. And going way back to the beginning questions about the platinum caps, I think the next one I do on here, I would make sure I have more platinum. You see, I lost my platinum cap before I got this thin, and that as soon as I lost the capping layer, that's when this started to go bad really fast. So maybe another micron or two of that capping layer would have been a good idea. Go back and try it again. But unfortunately, you have to just try on your sample and come up with a recipe that works. Especially with the plasma fib. The gallium fib, I think, is more predictable in terms of how it's going to cut, just because all materials cut real similar with that beam. With the plasma fib, there's a real big difference between stuff. Like carbon is really hard to cut. Metals seem to cut fairly easy on the plasma fib, and it's like the opposite almost on the gallium fib. So I will. This was the last thing I really want to show here. I'm going to call this sample done. You could do a 2 kV polish on it as well. So the fib will drop down to 2 kV, and you could run the pattern on each side for a few seconds, but I don't really see the point on this sample. I will undoubtedly do more of these demonstrations in the future, and hopefully the next one goes a little prettier than this one. But come find me if you have any questions on doing this. I'd be happy to try to help come up with conditions for your own samples. But if you have any questions, ask them away. I'm going to start venting the chamber, and then once this sample's out, I'm going to sign off. So if you have any questions, now's the time.
Yep, it was pretty clear. So yeah, I have used FIB before using the other Helios. So
Yeah.
It was pretty much the same, but yeah.
Yeah.
Just few tricks. Yep.
Yeah, those spiky little artifacts that show up on the sides, that's like the biggest challenge I find with the plasma fib is dealing with those. Because those things show up out of nowhere, and then they'll cut your sample in half if you're not careful.
Mm-hmm.
Which you can kind of see, right? That those little striations, they turn into these little crevices, and they'll just drop down, and your sample will be in 2 pieces before you know it.
Yep.
So they're frustrating, and the only really way to deal with it is either more platinum, more carbon on the top, or cut with smaller beam current. And like I said, I was in a hurry. I should have probably stopped and said I'm just gonna not finish this sample, but it is what it is. You can definitely make a whole lift out in like an hour and a half, 2 hours on the PFIB, even without being in a hurry. We lost a lot of time because I had to change the easylift needle. I wasn't planning on that one for my time budget here. All right. Well, if you don't have any other questions, I think I'm gonna sign off here, and I gotta shut down the tool for my next demo actually. So.
Got it. Okay.
All
Yep.
right.
Thank you so much.
Yep. Thanks for watching, both of you. All right.
Yep.
Yep. Bye.
Bye.